Hello. 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 Nikita ma'am. નથી audible? દીપક ભાઈ માઇક આમાં એ hello. Hello. Am I audible? Hello. 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 Am I audible?
Hello. Hello. 1 2 3 1 2 3. Hmm. हेलो मनाली में वॉइस ऑडिबल છે?
Yes, ma'am, it is audible.
ઓકે થેન્ક યુ. All the participants are informed. To kindly unmute their mic.
Yes.
Good morning, everyone. Soon we are about to begin with live online quiz for registered participants. Kindly stay connected. First, we will begin with live online quiz for school students and then for college students.
All the participants are. Ma'am, just I want to announce one thing. All the participants are requested to rename.
All participants are requested to rename Oppo F11 जिसका भी है, आप प्लीज अपने आप को रीनेम करो ताकि हम आपको आइडेंटिफाई करें कि किसने ज्वाइन किया है जूम में।
Okay, see, I'm going to quickly show you how to rename yourself. ठीक है ना? आपने अलग अलग नाम रखे हुए हैं जिससे हमें पता नहीं चल रहा कि आप कौन हैं, right? In that case, what do you do? मेरा स्क्रीन आपको अभी विजिबल होगा, right? तो जिस तरह से ये मेरा अकाउंट है, right? डॉक्टर दर्शन देसाई. So you can click here and you will have an option to rename, right? उस पे अगर आप रीनेम करते हैं तो you will be able to change your name accordingly. ठीक है, दिस इज हाउ यू चेंज इट. ठीक है ना, प्लीज टेढ़े मेढ़े नाम मत रखिए, वी आर नॉट एबल टू आइडेंटिफाई यू. सो नो, a request to all the participants to rename themselves.
A very good morning to each and everyone present here. On behalf of Mehsana Urban Institute of Sciences, Ganpat University, I, Ms. Nikita Chawda, extend a warm welcome to everyone joining us for Antrix 2022 on theme India's contribution to space exploration. Now, we will begin with the live online quiz for registered participants. The screen is already being shared. First, we will have the live online quiz for school students. Okay, students, you have to write the correct answer in the chat box. Whoever will answer first will be given points. Okay, so we will track it, and then at the end, during closing ceremony, we will announce the results. So this is the first question. Dr. Vikram Sarabhai is known as father of the
Dear participants, only those who have registered will be allowed to answer. The rest are not supposed to write in the chat window. Okay? The rest will be visitors or the audience, right? The only ones who will be participating are the ones who have registered for this quiz and have attended round 1 that happened on 8th of August. This is round 2. Okay, so and another thing is you should not put your answer more than once. Okay, please keep these things in mind. All right, we can move on to the next question, Nikita madam.
Yes. Can we have the next question, please? So the second question is, identify the person in the photograph. I request only the registered participants for round 2 of quiz to give the answers. Okay, moving to the next question. When was Dr. Vikram Sarabhai born? And these questions are only for school students. College students are requested to kindly wait. There are other questions for you people, which will be displayed soon. Yes, can we have the next question, please? One wants Individuals who do not have a compelling need to reassure themselves that they are leaders, Dr. Vikram Sarabhai. Next question, please. Who is with Dr. Vikram Sarabhai in this famous picture? Next question. Was Dr. Sarabhai nominated as scientific chairman of United States? Next question, sir. When did Dr. Vikram Sarabhai launch first sounding rocket from Thamba? Next question.
Hello, sir. No voice.
Able sir, either it can be played on cell phone and relayed here, or we can skip this question.
Okay, sir. Next question. When did Vikram Sarabhai establish the Community Science Center? Next question. Which was the highest civilian award ever given to Dr. Vikram Sarabhai? Next question, please. Which of these institutions was not established by Dr. Vikram Sarabhai? Next question. So with this, now we are concluding the live online quiz for school students, and now we will begin the same quiz for college, university level students. As informed earlier, this quiz is only for the registered participants who had participated in round 1 of live quiz. This is round 2. So other students are not required to answer any questions. Only the registered participants will write the correct answer in the chat box. So I hope all the registered participants from college, university are ready for the quiz. Can we have the first question, please? Who was the PhD advisor of Dr. Vikram Sarabhai?
Ma'am, just wait for 1 minute. The student having name of iPhone, please rename your device. आईफोन के नाम से जिसमें आपका डिवाइस का नाम है, प्लीज आप उसको रीनेम कर दो अपने नाम से. Continue.
Okay, ma'am. Next question, please. What literature is cosmic ray investigations in tropical latitudes? Next question. What was Dr. Sarabhai doing in this famous photograph? Next question. Name the first satellite put in space by the team with Dr. Vikram Sarabhai. Next, name the one and only doctoral student of Dr. Vikram Sarabhai. Next, when did Indian Postal Service create first stamp of Sarabhai? Next, the benefits of the uses of outer space treaty occur only through international, said by Dr. Vikram Sarabhai. Next, which of the scientists played a great role with Dr. Vikram Sarabhai in the launch of first sounding rocket from Tumba? Next, what was the title of Vikram Sarabhai's first scientific paper and when was it published? Next, which scientific instrument did Dr. Sarabhai extensively use for his PhD work? Next question, please. This will be the last question. The Vikram Sarabhai Journalism Award in Space Science, Technology and Research was first given by Okay, dear participants. So this was the last question of live online quiz. So now, participants, you can take break of 30 minutes. We will be resuming back for the webinar at 12:45.
Thank you, ma'am.
Thank you, madam.
Curious about knowing the basics of living organisms? Microbiology has all your answers.
Do you hear the call of flora? the chance to study the modern botany is all waiting for you.
The study of the chemistry is basically the theory of everything.
Expand your imagination through the brilliant ideas which will eventually formulate your future.
Dive into the unique realm of mathematics and be the gateway to solve the difficulties that's bugging the world for years.
Technology empowers humans, where biotechnology transforms them. Be the transformation you want to bring in the world.
Ever wondered how actual physics apply to the world we live in? Come to the home of physics and know how.
Ganpat University, Mehsana Urban Institute of Sciences empowers you to convert your passion and aspirations. As a result, you will be ahead of others in knowledge, practical hands-on, and logic. The modern infrastructure of Ganpat University, with all the latest instruments in labs, enhance your overall learning experience while you are being prepared for your exciting career. The experienced teachers, lay a strong foundation of domain knowledge within your intellect and make it easy to learn a variety of topics. From quantum mechanics to the latest inventions and discoveries that are making our world a better place to live.
Ganpat University aims at the all-round and holistic development of the students. The modern infrastructure, well-equipped laboratories and excellent teaching learning processes facilitate students to enhance their knowledge. The innovative academic processes evoke intellectual curiosity among the students.
Join the Ganpat University, Mehsana Urban Institute of Sciences to pursue your undergraduate and postgraduate programs in physics, microbiology, botany, biotechnology, mathematics, chemistry, etc. The institute also offers integrated dual degree programs. Do not wait before it's too late. Take a first step towards shaping your satisfying and successful career by joining Ganpat University, Mehsana Urban Institute of Sciences. Ganpat University is a forward-thinking and socially responsible university where students meet success.
Good afternoon, everyone. With the permission of all the panelists, shall we begin today's event?
Yes, ma'am. Please begin.
A very good afternoon to each and everyone. The dignitaries, invited guests, coordinators of various departments, faculty members, and dear participants. On behalf of Mehsana Urban Institute of Sciences, Ganpat University, I, Ms. Nikita Chawda, extend a warm welcome to everyone joining us for Antrix 2022 on theme India's contribution to space exploration. To grace this event, we have with us our esteemed speakers for today, Dr. B.S. Munjal, Scientist, Engineer G, Mechanical Engineering Systems Area, and Group Director, Structures and Thermal Group at SEC ISRO Ahmedabad. Dr. Abhijit Chakrabarti, Professor and Head of the Astronomy and Astrophysics Division and Project Director, PRL Ahmedabad. Dr. Amit Parikh, Dean, Faculty of Science and Principal MUIS, Ganpat University. Antrix 2022 is organized with the aim of celebrating 103rd birth anniversary of the visionary, scientist, industrialist, institution builder, Dr. Vikram Sarabhai, known for his unparalleled contribution to science. Making India believe that the sky is the limit, Dr. Sarabhai is not only credited for putting the first Indian satellite in orbit, but also for establishing the Indian Space Research Organization. He was instrumental in establishing the Physical Research Laboratory in Ahmedabad and also chairman of the Atomic Energy Commission. For his contribution, he was honored with the Padma Bhushan in 1966 and Padma Vibhushan in 1972. So let's remember and offer tribute to Dr. Vikram Sarabhai on this very special day. With this, I would like to invite Dr. Amit Parikh sir, Dean, Faculty of Science and Principal MUIS Ganpat University for welcome address. Please, sir.
Hello, good afternoon, everyone.
Good afternoon, sir.
It's a matter of great privilege and honor for me to extend a hearty welcome to all of you today on this occasion of celebrating 103rd birth anniversary of Dr. Vikram Sarabhai. In the name of today's event called Antrix, based on the defined theme, with immense admiration and affection, let me welcome our distinguished guest, Dr. B.S. Munjal, sir, Group Director, Space Application Center, ISRO, Ahmedabad, and Professor Abhijit Chakrabarti, Professor and Head of Astronomy and Astrophysics Division, and Project Director, Physical Research Laboratory, Ahmedabad. I welcome all the faculty members, students who made these efforts to join this ceremony in online mode. I heartily welcome and congratulate all the participants for their active participation in the various theme-based, model-based, and knowledge-based competitions. As per the tradition of Mason Urban Institute of Sciences, to celebrate days of national importance, we have been celebrating Dr. Vikram Sarabhai's birth anniversary since long. And last year, we have named this event as Antrix. And we are going to continue to celebrate this event by the same name every year. The core motive of the college to organize such an event is to enlighten the young minds and promote the participation of students at all levels. On today's auspicious day, I take the opportunity to pay my tribute to Dr. Sarabhai, the great visionary son of India. There are some people whose life and deeds lift our spirits. Dr. Vikram Sarabhai, the father of Indian space program, is one of them. A man of singular charm, he was full of humility, yet huge achievements. He was a world-class scientist, a policymaker, and also an institutional builder, a rarest of the rare combination, making India believe that the sky is the limit. Vikram Sarabhai is not only credited for putting the first Indian satellite Aryabhatta, but also for establishing the Indian Space Research Organization, ISRO. He was a man of uncanny ability and talent, dedicated to all the aspects of science and technology, especially space applications. His pioneering contribution towards the establishment and development of India's nuclear power plants for defense purposes. Apart from taking education to remote villages through satellite communication, landed him with two Indians' highest honor, the Padma Bhushan in 1966 and Padma Vibhushan in 1972, which was awarded posthumously. Hailing from the famous Sarabai's family of major industrialists who helped in the independence movement of India, Vikram Sarabhai founded the Physical Research Laboratory at Ahmedabad and Indian Institute of Management at Ahmedabad a decade later. One of the greatest achievements of the Cambridge doctorate holder was the establishment of the Indian National Committee for Space Research in 1962, which was the later renamed as the Indian Space Research Organization, ISRO. Once he famously said, "We must be second to none in the application of advanced technologies to the real problems of man and society." When India strives to become more Atmanirbhar in diverse sectors, we realize the significance of his words. He has also been rightly stated that the living conditions of the masses can be improved by creating institutions in which science and technology are properly nurtured. He was such an inspiration to young scientists of the country. Vikram Sarabhai's birth anniversary is also celebrated as National Remote Sensing Day in India. I would certainly state that all these offline and online competitions like balloon car race, parachute drive, space vehicle model, and quiz were organized to bring out the scientific approach of the students. Learning by experiments is the most effective tool for the learners to foster scientific thinking in them. Hope you all have gained hands-on experience in the field of learning science. I would also like to offer my regards to all the people who made this event successful. And for that, I compliment the Department of Physics for organizing this event. I wish you all a great success in your future endeavors. With all these words, I once again welcome our eminent resource persons of the event who have joined us today for giving their precious time. To conclude, I wish you all a great success in your pursuits. Thank you very much.
Thank you very much, sir. Now, I would take the opportunity to introduce our esteemed speaker for first webinar of today. Joining with us is Dr. B.S. Munjal. Sir is functionally designated as Group Director, Structural and Thermal Group, Mechanical Engineering Systems area, and is officiating as Scientist Engineer G in Space Applications Center, ISRO, Ahmedabad. Sir has 37 years of space research experience. Sir has filed 4 national patents to his credit as one of the principal investigators. One international patent is also in progress along with IIT Kanpur faculty for his research work in innovative reconfigurable antennas of spacecraft. Sir has been conferred upon K. Suryanarayan Rao Memorial Award for Smart Technology Development 2007 in the PhD investigation category by Indian Society for Advancement of Materials and Process Engineering, Bangalore. Sir is recipient of Excellent Paper Award in 11th International Collaboration Symposium on Information, Production and Systems, Waseda University, Japan, 2017. Sir has 2 books to his credit and more than 80 technical papers published in referred national and international journals of repute. Sir has guided more than 22 Master of Engineering students and 3 PhD students are currently working with him. With this, I welcome Sir and invite him for his talk on stretching the horizons of scientific research and applications from soil to space, an eye in sky for Atmanirbharta. Please, sir.
Hello.
Yes, sir.
Hello. Am I?
Yes, sir. You are audible.
Okay. My very good afternoon to this august audience. And I personally, in fact, congratulate Ganpat University for celebrating 103rd birth anniversary of Dr. Vikram Sarabhai Sahab. And I thank all the organizers for giving me this opportunity to interact with the young intellectual property of India, which is, joining in the webinar mode. I thank Dr. Darshan and Dr. Amit Parikh and all the faculty members for giving me this opportunity. At the outset, I would like to say that, as rightly mentioned by Dr. Amit Parikh ji, that the point that he noted was very correctly said by Dr. Vikram Sarabhai Sahab, and it is a motto for us also, that India should be second to none. That is very important. India should be second to none in using the advanced technologies for the solution of the real life problems of a common man. So we are, taught like that, we are trained like that to use the science as an application for solving the real life problems of a common man. Particularly speaking, the word, the science itself has to be, taken up in such a way that I would like to now start, because I have hardly 60 minutes with me. So I would just start with the PPT so that I can cover the slides with respect to whatever I have planned. I'm sharing the screen now. Okay, fine. Is the screen visible, please?
Yes, sir.
Okay. So as you have already mentioned, I thank the Master of Ceremony for telling the title, that is Stretching the Horizons of Scientific Research and Applications from Soil to Space with an Eye in Sky, the ground segment and space segment applications for Atmanirbharta for the India. Now, as you know, I have been telling on the 8th also, the very word science, which is, there, it is a beautiful word coined. If you really see the acronym, the full form stands for Scientific and Comprehensive Investigation for Natural Causes and Effects. It's a beautifully coined word, science. And we are, I am trying to stretch the horizons from the Mother Earth, that is soil, into the space. That's what our Dr. Vikram Sarabhai's project, was there in his mind, so that our own earth stations are there on the ground to receive and transmit the signals. And we have our own satellites, as mentioned by Parikh Saab, that we have our Aryabhatta as the first satellite. And then we have the concept of the airborne systems from the, concepts of materials point of view. So it's a full journey from S to S. Particularly speaking, I would like to mention that the point which you want to see as a technology, I would like to coin it as an eye in sky. So let us have a panoramic view, because in 60 minutes, I cannot cover the entire thing with full totality, but let's have a panoramic view with an eye in sky and proceed. Now, as you have seen, when we are talking of the space, we have to remember that we have to think big to think small. And this is the very concept of making the technology successful. That is why, according to Mr. Arthur, he from the JPL Space Inflatable Technology Lab, hello, is it now clear again?
Yes, sir, it is clear.
Okay, okay. In between, there was some connectivity problem.
Yes.
Now, when we are talking of the materials, which are, again, very important from the soil to space, we will be covering one by one the different aspects of this uh, material aspects also when we talk of soil to space. As we are considering the whole issue of science, we have to always keep in our mind that we have to capture the physics of the problem. That is why probably the Ganpat University Physics Department has really taken a nice initiative to really make us understand the physics of the soil to space. And I have already defined the word science. Now let us come to one or two, examples which I want to encourage all the students sitting here, that particularly with respect to the research, as I mentioned earlier also on 8th of August there, that research is not what you see, but it is to think what others have not thought of, because science and the research, they go hand in hand. And research is not what you see, but what you think and others have not thought of. So let us think from those angles which others have not thought of, and that is why you can file a patent on that. And that is why Professor Mashelkar, ex-director general of CISR, he in fact, coined a very famous statement, because all our MTech and PhD students, even we people, when we were doing our studies, we were told to publish the papers. Now he coined a very punchline that if you publish, you perish, but if you patent, you prosper. So we are trained in the ISRO that whatever comes to your, beautiful mind that is a brain, when we are talking, the more you keep it open, the more it works. So you have to keep in your mind that keep your mind open as a parachute. Now, Professor Mashelkar said, if you publish, you perish, but if you patent, you prosper. And that is why I insisted that whenever I visit Ganpat University, I talk about this patenting aspect, so that our all the new ideas and innovations, they are first filed as a idea, and then it is translated into a legitimate reality. Now, most important thing is, as I mentioned, the materials. And remember, the materials are the one which you have to keep in your mind, that right from soil to space, choice of the material becomes the most important. And now we have wide gamut of materials which are available to our skill sets. So we have to really make a wise decision, like an engineer, scientist, to use the right material and learn lot of things from the nature. Because nature is really perfect. God has made a perfect nature, but man strives hard to achieve that perfection. But remember, at the same time, we are human beings. To err is a human. So it is also said for human beings, strive hard for perfection, but be happy with excellence. So whatever is the journey of research, it is when our work is satisfactory and felt excellent, you are given PhD degrees or master's degrees. Further scope of work further improves it, and that's how the cycle keeps on continuing. The very first lesson, the lesson taught by our spider is a beautiful spider web, which can take the load which is much more than its own weight. So we can really take a lot of lessons, and that is why the Japanese people were first to coin the word biomimic. Biomimic structures, that is basically made up of the materials which can mimic like human beings. And in future you will find all these applications will talk of biomimic materials, which has lot of scope of work, which Japanese have given us a target to achieve the options in the Gaganyaan, Mars missions, and so many things. Now, just for the curiosity's sake, I would like to go to the curiosity itself and tell you something about the Mars mission. This is what is the NASA's Mars mission, which you can see. If the audio and video is coming properly, you will be able to really appreciate the background music of that. And this is the one which particularly takes 7.5 months as per their testing, and see one by one how in fact they separation takes place. This is the Mars mission, which is the NASA's Mars mission as an example to enthuse our children, for which the India is also following it up. And I am giving the parallel commentary to this because you will understand stage by stage how beautifully this process takes place. And remember that the success of a mission comes, which is basically after 8.5 months, you will find that everything works in tandem, and that is why this mission becomes successful. Now you see how in fact it is getting lowered after 8.5 months. This is the device which is approaching the Mars mission, and see, the point is it's a totally inclement weather and the temperatures are totally unknown, and there you find how in fact this particular device is now facing the load, which is the friction load, and it is glowing, that is, it is burning, and all the materials have to be chosen which sustains this severe temperature. And remember that how in fact we will be able to demonstrate in the NASA video that how this particular thing will lower the a parachute, which you will see now, which will be carrying the rover. You see, the parachute is lowering down one more than 1700 to 2000 kg vehicle, which is lowering on the surface of the Mars. Just concentrate on this video. See, somebody was asking me a question. Somebody was asking me a question on 8th in the school, that how this will be balancing. You see how this bottom exhaust which is coming up is balancing the rover on the Martian surface, and then it is preventing it to get spoiled or get toppled on the surface of the Mars. See how gently it will lower down. And see how the vehicle is going down. These are rovers. Beautifully, the wheels are lowered, and this wheel is made up of all the smart structures which I will be telling you. Now the vehicle is rolling. Again, concentrate how it will have the landing. Now this is disappearing after doing the work, and you see the vehicle now. With all the remote signals, using the space signals, now the ground operations from NASA, they are able to maneuver this vehicle. I saw one model also made by the students of the Ganpat University. I want to congratulate them for their thought, that how nicely they had come out with the intricacies and the nitty-gritty of the model. And then I told them, I promised them that I'll be explaining how the multi-institutional and multi-physics based approaches are there, so that we are able to see not only the thermomechanical, thermo-optical, structural optimizations, and then the optomechanical approaches in the camera structures which are loaded on that, and how the unbalanced torque is balanced by the smart wheels. You see how the camera is getting oriented in the roll, pitch and yaw direction. And it is going to go to a place where you will find that it has to collect the sample. All the coordinates are set by the remote approach. You see how gently it will now start moving. These are called celestial coordinates. When you have the x, y, z, rotation x, rotation y, rotation z, and x dash, y dash, z dash, and all these 6 degrees of freedom in the space. You see it has started moving, and all these wheels are made up of smart materials which are balancing the unbalanced torque by changing the orientation of the wheels, so that it is not toppling down far away from the Mother Earth. Now, let us come to the next video. This is in fact, I found some of the students, making the models, and then when I was asking the question, what is the difference between PSLV, GSLV? So I told them that if your question is still not answered, I will explain you that all the remote sensing satellites are moving from north to south. They are launched using polar satellite launch vehicle, and even the remote sensing satellites, and then the Mausam Vibhag is able to use these satellites, and all the geostationary satellites are above the equator at about 36,000 kilometers as per Sir Arthur Clarke's invention. And it is there because it is in a geostationary orbit. He coined the idea that if you lock the satellite above the equator, it will always remain stationary on a given landmass, because the movement of the Earth, our Mother Earth, and the satellite is geosynchronized. That's why it's geosynchronous satellite. And polar launch vehicle launches at 900 kilometers, which is in the orbit in the north to south pole, for all the remote sensing applications, for finding out the soil related details, and then the crop related details, and then the storm and tempest related details, and then the disaster warning system of our India works to save our fishermen and all the other ships which are in distress. Now remember friends, this is a bit of definitions, but particularly as you know that space problems are all non-linear problems, and non-linear material related, real stress strain curves come into the picture. All my engineering friends will be able to appreciate that instead of stress strain curves, we have true stress strain curves which are coming up. And all these, Indian remote sensing satellites and IRNSS satellites which are there are using these smart materials, and then the materials called indium, particularly for developing the clock, which is used by RNSS. But I will not go into the details because of the time crunch. And particularly speaking, now we are talking of the next slide. Now, why I am showing you this example, because I will show you to generate interest in the students, that you can learn a lot from the mother nature. I also, during my PhD project, you can see the first slide, which was I started working when only one professor in the Ohio State University was working as a Professor Gregory was working on that. I interacted with him. He worked on a polycarbonate material, and I started working on a space qualified material after my space application center qualified that material as a PEEK, that is a polyether ether ketone nano material pumped and impregnated into the carbon matrix to open the satellite reflector like our beautiful rose, that is like a flower, which was later on given a patent, and we coined the locking mechanism for it with IIT Kanpur. That also has been patented. And now you can see all our departments, drones and other DRDOs type of thing, army applications are learning lot of lessons from these dragonflies, how in fact you can generate a helicopter which can be simulating the applications of a dragonfly. Particularly speaking, I remember when Mr. Bolden, he came to Space Application Center, ex-NASA administrator, with, perfect body language. He gave us a challenge, which I told on 8th August also at Garpat University. I, in fact, recalled, because the chill ran down our spine at that time when he said, look, gentlemen, very frankly, I'm telling you, what I need is a 1 kilogram helicopter with a wingspan of hardly 1 meters. Can you give me? This was a challenge thrown, 1,000-gram helicopter with a wingspan of only 1 meter, so that I can use it for interstellar missions. My God, friends, the chill ran down the spine. We were sweating virtually in the AC hall. which technology we will use. Are we geared up for that? Atmanirbharta, I am thankful to our Prime Minister that we are now given new dimensions in the form of NSIL and InSpace, and ISRO is opening up particularly to have handshake with the research department, academic world, industry, so that our perfect equilateral triangle works and we work on a NASA model. Anyhow, now these are the lessons learned from the dragonflies, and last one I will show you the video one by one. You will enjoy the part, particularly this work, that when I visited NAL Bangalore, particularly in early 2000, that is the National Aeronautics Lab. I found professors at that time who shook hands with me. They were working on developing aircraft which is having the concept of taking off like an eagle itself. Why to have a runway of 2 kilometers, and why can't we take off in tomorrow's aircraft almost like an eagle? So one by one, you see the God's challenge given to us is we can have such a big dome without any pillar. See, these are marvelous things which God has given. Let us see one by one. I will not spend much time on videos, but you will get a feel of it so that I can cover all the slides. Okay, fine. What you see, friends, that this is an actual dragonfly which is going, and we have to learn a lesson to develop a helicopter with wingspan of 1 meter. Now let me show you another video before I run short of time. You see, this is the video.
कितना कहीं में हमारा बैग में मिल
Friends, actually thing is that when you really get up in the morning, I told on 8th August that this is the beautiful thing that nature gives us fresh vibes, and you find that flowers unfurling at the same time. You will find sunflower orienting towards sun, and the birds start chirping. Remember that a researcher and a scientist derives lot of lessons from the mother earth and gets rejuvenated by visiting nature. So next video which I am showing you for some time is the eagle, which is taking up. Now carefully watch how the eagle takes off. You will find this eagle will sit on a branch and then without any runway, it will take off. Dr. Abdul Kalam Saab also, our late Honorable President of India and our missile man, he in fact, said that I got the lesson from my own professor and teacher who used to tell me. You see how it has taken off. So tomorrow's aircraft, if they are able to take up like this, you can imagine that NAL started this. If you visit anytime, you can see the work going on. In brief, I can say you, because it's a full subject of smart materials and smart technologies, which it has to be given initiative in all the departments, so that the new materials like nickel titanium alloys, and then we have magnetorestrictive materials, we have electrorheological fluids, we have magnetorheological fluids, so on and so forth. So what I feel is that if the wings are having the material which is made up of nitinol, that is called flexinol in the market for different temperature ranges. It can be trained in the austenite and martensite state, that is in the hot case and cold case, because space temperatures are very, very high, that is about minus 120 to plus 120 degrees, the steep temperature gradient. And those materials, you will find that first they are cleared for the spacecraft, then they come back to the aircraft, then they come to the automobile industry, about which one video will be shown, and then you will find that those applications will come to the soil, that is the applications for our buildings. So you will find the journey starts in 4 stages, from space to air to buildings. This is the journey which is moving, so that the materials also go on changing. Now let us see one by one this approach. You will find that these applications we have discussed, and now we are going to tell you something about the materials which are there as a, you know, antenna or earth station materials, which are generated using the, you know, technology, where you will find that this earth station receives and transmits the signal from the satellites. It is having a very important role, very stringent specifications, and all the mechanical structures, civil, instrumentation, electronics, and all the multidisciplinary fields are there, because the RF engineers, the radio frequency engineers, their work is not super visible here, but all the invisible signals which are coming from the satellite is their, you know, contribution. So remember, it is a total team effort. That is why we are taught like this, that where there is a team, there is a steam. But remember, where there's a team and steam, remember the country's esteem lies in that. You will appreciate this is country's esteem to become Atmanirbhar, right from soil to space. And these are the earth stations. What you find is the backup structure, the reflector, the mount, the soil, the raft. That is all these things designed for accuracies to the extent of, you know, pointing errors to the extent of few arc degrees. And if it is converted into telescopes, the accuracies are even more stringent for, you know, few arc seconds. That is why you will find Chakrabarti sir talking about the astrophysics and astronomy, you know, subject. I have worked with him for 3-4 years on the project of Mount Abu. I know that how much it was, you know, difficult for us to really design the holistic analysis, particularly when the soil was not there and the whole thing had to sit on the Guru Shikhar, which was a rock. And it is in the zone 4 of the IS 1893, and with a horizontal seismic coefficient of 0.04. So remember that for that type of, you know, inclement conditions, we had to design that holistic analysis using the approach called finite element analysis. So this aspect I leave it to him for covering. I go to the next one. This is, in fact, you know, you find the finite element analysis done particularly for the complete soil model, because you know the soil also at various places. When you move from Leh Ladakh, our telescope is coming up there, to the southern peninsula, and then to on the eastern side you go to all Machilipatnam and Vishakhapatnam areas. On the western side you go up to all the Saurashtra regions. You find different soil conditions, and for that detailed finite element analysis and geotechnical investigations are done, which I may not cover in detail. But yes, it is a full ocean. All the subjects are nowadays an ocean, and you start from the, you know, space sciences, and even the Gagannauts who will go into the space, even the food sciences. I have been mentioning in the Ganpat University the, you know, effort required to really start the space food for our Gagannauts, which is there almost in the future. And our Indian Institute of Sciences Bangalore has already tied up with our Mysore Institute, so that they come out with the space food also. Now these are a different, you know, ground segment applications, which one by one I think particularly in this Guru Shikhar part, which is more stringent in this, will be covered by Chakrabarti Saab. You will find that in ground, you will find these applications of the, from the earthquake point of view also. When the Latur earthquake came in the ISRO, we were told at that time to find out the post-earthquake damage assessment into our Earth station antennas. At that time, we coined the idea of putting strip sensors in the foundation so that the new subject of SHM, structural health monitoring, starts. And we started taking initiative in this domain. Even the bridge structures and bridge fires and stanchions can be taken care as a SHM field, structural health monitoring. Particularly speaking, the telescope mirrors, which are very important, which our Chakrabarti Saab will also cover as one of the options as a zero door material, which we want a low alpha and low gamma material, that is the lowest coefficient of and lowest coefficient of thermal expansion and hygroscopic expansion. Okay, now let's have a look in the automobile. Friends, you must have watched this Tarzan the Wonder movie, but you must be recalling that how the car automatically gets repaired using the smart technologies, and how we can dream of having one penicillin type of tube which you can apply on the dent of a car, and next morning it the dent is automatically cured. That's really a dream project. But yes, smart materials are giving us an opportunity so that we are able to develop the materials for the automobiles also. Now you see the materials which are required in space are high specific stiffness material, that is the modulus of elasticity to density ratio should be high. It should be having the one which is strength to weight ratio should be also considerably low, so that we are able to use the material in the space domain as well as aircraft domain, and then to the ground domain. So you will find this revolutionary materials like Xylon, Torlon, polyethylene ketone, and carbon nanotubes. Our all material friends in the Ganpati University must be really aware of chirals and carbon nanotubes, how much work is going on, and one or two by PhD students are also working on this for developing the applications in the space domain. This is our satellite where the applications of smart materials are done in the solar flap, so that it balances the unbalanced torque of the satellite into the space, so that it maintains the in the right orbit. Now these are the different applications in the reflector and the ribs domain using piezo patches and all. I need not go into the depth of it, but I would like to tell you it is having applications in the launch vehicles, particularly as well as aircraft. So that where I was asking the question also on air, that where is the satellite? Now our friends will remember that the satellite is sitting in the nozzle here, which is a heat shield. And the last stage is this. I will demonstrate you to in a video also. Now you will find that basically what happens is that the vibration loads are more important in space where during the launch, and post launch you have micro vibrations due to movement of gyros for the stability purpose and the roll pitch and yaw directions. But the point is that the thermal loads are very high, micro vibrations and with combination of thermal loads. When we come to the ground, we have here wind load, we have earthquake load, superimposed load, and so on and so forth, load combinations. You see this video now carefully. I will just explain you. Friends, you have watched the video many times, particularly on the TV also. But if I give a commentary, you will really appreciate and go to the depth of it for 1 minute or so. You see, right now the rocket, you can see any PSLV or GSLV rocket is in a stationary state, and it is before ignition. Ignition will take place somewhere here. Now, what you will do is you will notice that from static, it will go to quasi-static, just like static. But at that time, the weight of the rocket W and the thrust generated because of ignition is just balancing in a dynamic situation. And then it goes to a transient stage, and then it is going to steady state stage, which is, for a smaller launch vehicles, it is generating accelerations of 6G, 6G and 10G. G is gravity. It will experience more weight. That is why it is said the G loads. And you will find that when we are going into the space, our rockets, they are subjected to severe vibration loads. Even if the launch vehicle is a bigger one like GSLV, it is 20 and 30 type of load, 20G, 20G and 30G. 20G in plane both the sides, and Z axis 30G. So you can understand how much the payloads have to undergo, and that's why the series of tests are done. I gave it in your college one book which I authored for children particularly, so that our children come to know about the concepts which are there when the satellites and the launch vehicles talk to the scientists that what you are doing with me, why are you testing me so severely. So it is like giving a feeling to this and making the children understand what is the dialogue going on between the structures as well as the scientists. Okay, now just have another look at it and listen to me. What is going on? It is about to get ignited. There is almost countdown going on, and all your 9876 is going on, and there comes now the point zero. Now the zero comes, it is a quasi-static stage, and when the W is less than the thrust, then it takes off. For a period, it is a transient state, and now it is going to the steady state accelerations, and one by one the rocket parts will start falling into the ocean, and everything is working in tandem. You will find that the heat shield is separated, and the satellite which is sitting at the top of it is now going to get ejaculated at 7 kilometers per second to escape the Earth's gravity. And the moment it will escape, it has escaped now. And you will find that the satellite is now about to open the reflectors, which are carbon fiber reflectors. This is a longeron, and these are solar panels. So you will find that it is a system where fraction of nanoseconds also can have a mission failure. So this is a type of accuracy. On ground we are talking of several arc seconds type of accuracies for telescopes and arc degrees for the earth stations, whereas for satellites we are in the roll, pitch and yaw direction. Also we talk of all the stringent specifications, and the materials have to undergo all the series of tests, which I said that to the management that they can make our students visit the Vikram Sarabhai exhibition near the ISRO for a full day program, where you will see the live models which are there demonstrating these technologies. Now let us this noise damping is also one of the phenomena. I have a few minutes left, so I will not go to the detail of it, because I have to leave some time for the question answers also. There are various applications in the Center for Airborne Systems which came out with the applications when the Brahmaputra river had a flash flood, and they developed the terphenol D rod smart material based antenna, which was put at the fuselage of the aircraft. These are futuristic large deployable reflectors, which will be that the futuristic boom will be moving from M boom to E boom. Now, our present satellite reflectors are 1 meter to 2 meter. We will be having futuristic applications of 13 to 30 meter. for which the shape corrections to get the right RMS of the surface, root mean square surface, we will have to use these piezo materials to balance the deformities in the structure. And these are the applications of, who will repair it. So we have the new concept of, embedding these dicyclobentadine capsules into the solar panels, so that when they face the crack or crack propagation, complete fatigue analysis can be done for this, so that the crack gets filled up by bursting the betadine capsules, and then the self-healing of the spacecraft takes place. And futuristic reflectors may not be made up of carbon fiber or Kevlar fiber, but we may have inflatable type of structures which will be covering larger diameters. Even NASA's recent studies on the space solar power satellites were generating large amounts of electricity from large scale space-based solar power systems is also in progress. New materials are there from reducing the damping of the reflectors, which is also, you find the attenuated values are lower than the actual amplitudes. And you will find the domain of nanomaterials has picked up like anything, which is applications right from the fabric which our human beings are using, or the ladies are using in saris, to the jackets and coats, and right from the applications of micro, nano, pico. Pico is 10 raised to the minus 12, femto 10 raised to the minus 15, atto 10 raised to the minus 18, right up to the zocto technologies, 10 raised to the minus 24. You will find that human body is already working. You see your own human body, it is almost zocto technologies God has put in the form of chromosomes and genes and DNA, RNA, whatnot. So we have, as rightly mentioned by our Amit Parikh Saab, that the sky is the limit. I will say space is the limit nowadays. So these carbon nanotubes, which are chirals, are giving us the futuristic, applications, because I remember that it was told in one of the conferences, the futuristic money spinning industry will be space industry, and all the money will come from space domain. So already people are there who are using, graphene material, that is a single wall, double wall, for getting the strength up the steel as superconductive material, which is there almost 200 times stronger than the structural steel we are using on the ground for these applications. And soldiers are also using this material, which is in the form of bulletproof graphene jackets and other things. Even new concepts of the space domain, which is a thought-provoking, idea for all of us, and we have to really take it up, is that frozen smoke structures, which are built out of polymers and metals and ceramics. Because remember, the boundaries have to be transcended from the mechanical structures, civil, to basic lines, to all the combinations and multidisciplinary lines like thermomechanical, thermo-optical, optomechanical, instrumentation embedded into that, electronics embedded into that, civil applications embedded into that. And then comes the problem, which has all the solutions. That's why it is a, researchers say that beat the problem, greet the problem, and defeat the problem. Only when you work as a team, you can defeat the problem. And this is frozen smoke structures, which is almost 160,000 times, it can withstand its own weight. So remember the spider, and then now this frozen smoke structures are almost going in line with that. This is what you see as a carbon, based, carbon nano based applications right from soil to space. Because I remember, in future, in one of the conferences, they already mentioned that people and children will not go to some hill stations, and they say we'll go to Leh and we'll go to Switzerland. And they say simply let us go to lower Earth orbit, where our International Space Station is there, ISS. And then we will have the space odysseys. And this is the carbon nanotube based, new concept of space elevators. This is what I will not take much time, but I will show you one of the smart materials, how it changes from spring to different, different shapes, and after heating, because it is trained, it will come back to its own place. See, now it is heated, and you will find that it is taking the shape back. So these are beautiful examples of the materials. This is another example, but I need not have time. This is another example, but I will run short of time. Now, thing is, the various applications, I'll run through the slides so that I get some time for question answer. Now, thing is, one particular slide I want to cover. Our Indian Plasma Research Center came to a rescue for space problems when we were struggling, and we how to in fact metalize, because all these reflectors are metal, so carbon fiber may allow the penetration of high frequency signal. So we wanted a metallization on the hydrophobic surface, and how they deposited the using the Menton sputtering, how they deposited the copper material for few angstrom to get the transmission and receiving possible of high signals. You see, this is a typical slide of plasma, which is a IPR-based approach of Facilitation Center for Industrial Plasma Technologies, which you will find this plasma is getting deposited on this dish. I have told management that they will be taking you to the tokamak, which is there in our IPR Gandhinagar, because we are coming out with a robotic arm as a committee member in that. And this is going to give you an idea of how we can have the futuristic plasma applications, which are there particularly in the daily man's day-to-day activities. Plasma will come to a rescue. I have a separate book on that, which I have already discussed earlier with management. And these are different examples of the smart materials which are going on in the lab, which I need not cover the details. Yes, this is a typical type of vibration shakers, which you will study later, particularly for MTech and PhD students, that how the vibration loads of a launch vehicle are simulated on the ground itself, and then they are almost tested like our heart is getting tested, and then they are our reliability and quality assurance will clear the product for space launch. This is a lab which is a compact antenna test range where all the space related simulations are done for the satellite reflectors. So from soil to space, we are sitting on the soil and then testing the materials for the space. It has various applications, as I told you, from soil to space. We have the applications in the domain of machining, telecom, aeronautic, automotive, instruments, medical world, n number of applications in orthodontics and medical world. Even the smart materials are embedded in the angiography and angioplasty operations, where the stents are developed using the nitinol. These are the different space positioning mechanisms which are there. Now I will try to conclude by our Dr. Abdul Kalam Saab's statement. He always used to say that difficulties in your life do not come to destroy you. Remember, we get scared, but they are to help you realize your hidden potential and power. So friends, So friends, I would like to end here. And Professor McEwan said, that half of the life of space scientists is spent in waiting for their realization of dreams, and yet their enthusiastic vibrations always remain undamped. Thank you and good luck.
Thank you very much, sir, for this elaborative session. We are very thankful to you for your time and presence and accepting our invitation for Antrix 2022.
Okay, madam. Thank you. So nice of you. Any questions, please?
Yes, students, if you have any questions, you can write down in the chat window. I would also like to invite Dr. Darshan Desai, Head Department of Physics, MUIS Ganpat University, to summarize the talk for today.
Well, good afternoon, sir, and
good afternoon,
good afternoon, everyone. It was really nice to hear your talk, and we understand now that there are a lot of there is a lot of scope, so to say, as far as research in these fields are concerned. So I hope all the students were able to understand the avenues for accomplishing more, from say advanced materials to robotics, right? There are a lot of things that remain to be done, and it is, we feel really grateful to be able to get in touch with the frontiers of the things that an esteemed institution like yours, sir, is working on. So, students, I hope you were able to grasp these things well, and try to read about these things more, and then you'll be able to contribute to these fields. These are current real challenges. And sir, thank you for also, thanks a lot for the arrangements that you said you will be making for us for the visit and all. My students, I believe, will be highly interested in exploring these fields even further. So we'll be looking forward to hearing you, sometime very soon again on plasma technology and various other things that we could learn from you, sir. So really grateful, and thanks a lot for being with us today.
So nice of you, friends.
Thank you, sir. And with this, I think I will hand over the session back to Nikita, madam.
I would like to say one thing, that for the students' benefit, that Robert Frost said that woods are lovely, dark and deep, but we have promises to keep, and miles to go before we sleep, and miles to go before we sleep. So I'm sure the students will take us, to the levels which was the dream of Dr. Vikram Sarabhai. Thank you and good luck.
Thank you, sir. Thank you.
We would like to present, yes.
Yes. So Nikita, madam, if there are no questions, on behalf of the institute, let us please present a statement. Sir, it is a very small token of gratitude from our side. So please accept this. Thank you, sir. And thank you, sir. It's really, sir. Your microphone is okay. Let me.
Hello. Yeah.
Right, sir. I can hear you now. So thank you, sir, for being with us, and hope to have you here in the future over and over again, sir. This is just a small token of gratitude. We just wanted to express our gratitude for all the contribution that you have made to this institution, as far as imparting education is concerned, and you know. Through talks like these, we try to connect the students, we try to form a bridge in between, the institution here and the real work that is being done outside the institution as well. So you have contributed a lot to that effort, and we are really grateful to you, sir.
So nice of you. Thank you very much. Because no science is like a rocket science. So that's why we have to simplify. I showed more videos so that something the students can carry home. Thank you and good luck.
Sure,
Have a
sir.
good day.
Very inspirational, sir. Thank you very much, sir. Thank you, sir. So with this, I think I'll hand over the session back to Nikita, madam. We can proceed for another talk. We have Dr. Abhijit Chakraborty, head of the department at academics and astrophysics division at PRL, and sir is also leading the project on 2.5-meter telescope, which is currently being installed at the Mount Abu Observatory, if I am not wrong, and with various other projects, of course. And we are also very eager to hear you, sir. So welcome, Abhijit, sir. And the session is
thank
over to
you.
you, sir. Thank you.
Yeah, I think my video is stopped, so and the
I reset the permissions. I hope.
Yeah. Okay.
Thanks, sir.
Okay. Yeah. So thank you very much for giving the opportunity to talk to the students of Ganpat University, and I appreciate very much for the interest that you people have in the work that is being done at PRL. So without wasting any further time, I will just straight away share my screen and start the talk.
Sure.
So we would like to give a short introduction.
Okay,
and then,
please go ahead.
Yes.
Please.
So we have with us a very eminent speaker for today's webinar, Professor Abhijit Chakraborty, sir. Sir did his PhD in PRL and obtained the degree from the Gujarat University, Ahmedabad, 1999. Sir joined PRL in May 2006, and presently he is heading the Astronomy and Astrophysics Division. Sir is the project director of the PRL 2.5M telescope and principal investigator of India's first dedicated program on exoplanets using high-resolution spectroscopy and velocimetry, which is responsible for both planet and star characterization. Sir's field of research interests are optical, near IR instrument design, high-contrast imaging with pupil plane optics and exoplanets, planetary systems, and stellar astrophysics. Sir initiated PRL Advanced Radial Velocity Abuskai Research PARAS program in 2008 at PRL as India's first dedicated exoplanet program. Sir received the 2019 Lunar and Planetary Science Society's Lecture Award given by Gujarat Science Academy for his discovery of an exoplanet using PARAS. With this, may I please welcome and invite Sir for his talk on Introduction to Astronomy and Astrophysics. Over to you, sir.
Thank you for the introduction. I appreciate it. So I will, when Dr. Darshan contacted me for a talk, I thought, I thought I will give a talk on the exoplanet research work that I am doing. But then I thought, because it is this talk is directed towards undergraduate students who are science graduate wants to be a science graduates or engineer graduates. I thought basics of astronomy and astrophysics will be more suitable. So first, my talk is basically distributed into two parts. The first part is basics of astronomy and astrophysics, where I mostly discuss about stars. And then in the later part, I will briefly touch upon the research on exoplanets that we're doing in India. Okay. Can you see my slide?
Yes, sir, it is visible.
Okay. Okay, so whenever we look at the sky in the night sky, if you look carefully, you can see the stars. Of course, today if you're living in cities like Ahmedabad or Mehsana, because of the street lights, you will not be able to see. But if you go to the villages where there are no street lights and the sky is relatively dark, and in the absence of the moonlight, you can see lots of stars. So, and if you take picture of those stars, you will yeah, those pictures nowadays, you have digital cameras, you can easily take pictures. But of course, you have to, like put it on some kind of a star tracker machine so that the star doesn't trail. So then you can see in the image that you can see in the background here, which clearly shows the colors of the stars. Okay, so basically, like since ancient times, we always wondered, humans, whenever they looked up the sky, they always wondered, looking up the sky, what they are, and the stars, they, since ancient times. And by the way, our calendar and are based on moon and which constellation they pass. So basically, like our timekeeping since ancient times has been based on our observations of the celestial objects in the sky. And that is how we came to understand the concept of time, which is very important in our life. Okay. And then, of course, the navigation part in earlier days when there were no satellite GPS and all, the shipping industry, the people who used to trade for thousands of years, they used to look up the sky and then decide which is north, which is south, which is east, which is west, and accordingly they used to, move their ships or boats. So to put it very briefly, that the concept of timekeeping, navigation, and of course the basic laws of physics that we came to know with from Newton and others physics, and which actually helped gave the rise of engineering, physics, and everything. They all actually started with observations of the sky and movement of celestial objects on the sky. So it is a very basic subject. Astronomy, astrophysics is a very basic subject. Okay, so when we so how do you know what the stars are? So what we are getting from star, we see light coming out of the star. So what are light? Light is basically, you can in modern day, like physics terminology, you can say that light are basically photons. Okay, so so when you are seeing photons or light waves coming from the stars, what you can derive from them? Because all you are getting from stars is light, nothing else, and they are very, very far away, thousands of light years away. So so how do you know what they are? So so when we like get the light from the stars, basically you can do two things from from this light. Either you can like you can devise an instrument by which you can basically try to understand that how many photons you are collecting from the star, from a particular star per second per unit area. It can be per centimeter square or per meter square. Okay, so when you try to get that number, that's called photometry. Okay, you can also do another thing, that is you can distribute the distribution of photons with respect to their frequency or wavelength, like whether how many photons that are coming from the light are blue wavelength or red wavelength or green wavelength or yellow wavelength. When you try to do that, what you do is spectroscopy. So here you can actually see that typical spectra of the star, like a rainbow, from Vibgyor kind of thing. And when you do that, then you get lot of information from them. So in the course of this lecture, I will try to show you what we can get and how we can classify the stars based on their brightness That is, if you get more number of photons per second from a star, it is compared to another star which is giving us lesser number of photons per second, which means that the one that is giving more photons is a more brighter star, the other one is a less bright star. Okay, so like characteristically, today we have digital cameras, we have CCD, scientific CCDs, we have so much of electronic devices by which you can collect the light, measure them, and you can digitize them, and you can get the numbers. But think of like a couple of 100 years back or even 100 years back, okay, when these kind of scientific instruments were not available, the only way one can actually measure the star brightness was the human eye itself when you look up at the sky. So what happens is that when such a thing happens, you are basically using the human eye as your detector. Now, human eye, because of the evolutionary reason, has a logarithmic response. That is, you can in the night you can see very faint light. At the same time, in the daytime, you can see under the sun, you can see very bright light. So this kind of wide range of light distribution is only possible if your eye has a logarithmic response. So therefore, when human beings started and about 100 or 150 years back, trying to quantify the brightness of the stars, they realized that, they said that, okay, the brightest star may be called as 0 magnitude. The next faint star may be 1 magnitude. And then again, the next faint star may be 2nd magnitude. That is, the scale increases as the star is less and less bright. And so now if you want to put it in terms of mathematical response, so if one star is M1 and another magnitude of M1, another star is magnitude M2, then because I has a logarithmic response, it can be depicted like this. So where B1 and B2 are the number of photons you are receiving from M1 star, and B2 number of photons or brightness from M2 star. So you get difference between M2 and M1, that is delta M, that how much bright the star M1 is with respect to M2 is given by this number. Okay. So which means that if the number is negative, then the M1 is brighter than M2. If the number is positive, then M1 is fainter than M2, because the scale is reverse here. The other thing that also we would like to introduce is that the 1 by r square dependence, which means that if you have if you say, for example, if you have at home you have a table lamp and you are studying, near it, if you can trying to read something, you have to put the notebook or the book near the table lamp. If you go away from the table lamp, the amount of light falling on the paper or the book from the table lamp decreases, and therefore you may not be able to see the writing on it. And this the dependence is 1 by r square dependence, as is shown here. Okay, so that means if there are two stars, one is very bright, another is intrinsically bright, another is less bright. If the less bright star is nearer to you and the brighter star is far away from you, then it may be possible that the actually intrinsic less bright star will appear to you more bright than the actually intrinsically brighter star. So how do you like solve this issue? Because when we look at the sky, we exactly do not know how far they are. Okay, they are all projected on the sky plane, and so some star is very bright, and some star is appears to be bright, and some star appears to be faint. Like for example, this star appears very bright, whereas this star appears very faint. So, so in order to solve this problem, to understand intrinsically which star is more bright and which star is less bright, we do a hypothetical scenario where we put hypothetically all stars at equal distance from us. And that distance is considered to be 10 parsec, where 1 parsec is 3.26 light years. Okay, so so this concept is called absolute magnitude. The magnitude of the star at a distance of 10 parsec, or 30 light years away, is known as absolute magnitude. So by doing this, we are we are taking care of the distance factor, 1 by r square distance factor, and then we can actually say that which star is more bright and which star is less bright intrinsically. Okay, and the this capital M is denoted as absolute magnitude in terms of symbol. Okay, so next concept. So I talked about the the fact that we try to measure the number of photons per second coming from a particular star, and then compare it with another star. So typically, we do it in the optical range which runs from from violet to red, or even beyond red. So violet wavelength is around less than around 350 nanometers to 400 nanometers. Blue wavelength is from 400 to like about about 550 nanometers. The green or yellow band, which is known as V band, is from like around 480 nanometers to 650 nanometers, and then the R band, this curve, is from around 580 nanometers to about 800 nanometers, and then you have beyond red, which goes all the way about up to 1200 nanometers from 700 nanometers, is called the I band. So the reason such bands are chosen is because what we do is that, say for example, like you want to measure what is the amount of photons flux coming from particular star in this band, then you put a filter that has that only transmit the photons that are corresponding to these wavelengths, and so you can take that. Observe the brightness. The same star, if you want to observe in different filters, and in different filters you will get different intensity. And what do we get out of it? We get the following thing. You see, that from quantum mechanics that you have basically, like all body acts like a solid black body radiation. The concept of black body radiation was introduced in the year 1900, where what you can do is basically, like it's something like this. Suppose you take an iron ball and you put it in a gas burner. You will see first as it will get slowly hot, first it will become red in color. When it gets more hot, it will get slightly yellowish in color. If you further heat it, it will get green in color. If you even more heat, it will show bluish in color. That is the temperature of the black body, the iron ball, like is directly corresponding to the color of the body. Okay, so the blue light emitting body is more hotter than the red light emitting body. Okay, so So in order to determine the temperature of the star, these kind of filters have been designed so that like when you observe stars in these filters and compare the number of photons you are getting, and then you can, if you plot the curve, you can clearly draw this kind of black body curve like this. So, so obviously this is a very cool star. This is a hot star. It is a sun-like star, and this is a very hot star. Okay. So intensity of the light emitted by these three hypothetical stars is plotted as usual. The range of the visual wavelength is indicated. So, so this clearly demonstrates that by using these filters, observing these kind of filters, we can actually determine the temperature of the star, the surface temperature of the star, not the inside, the surface temperature. Okay. So based on this, we can do spectral classification of stars. Okay, so if the star is blue violet, then they are called O type stars. If they are blue white, then they are called B type stars. If they are white, they are A type stars. And where the temperature is about 7,500 to 11,000. In case of O type stars, is 30,000 to 50,000 Kelvin. B type stars 11,000 to 30,000. A type stars 7,500 to 11,000. F type stars 5,900 to 7,500. G type stars, like our sun is a G type yellow type star, so its surface temperature is 5,800, and typically G type stars temperature vary from 5,200 to 5,900 K. Then you have the orange type star, K type stars, which are called which can be 3,900 to 5,200, and finally M type stars, M DOS red, which temperature is 3,500 to 3,900. So so using those filters, simple technique of filters, and if you have a simple detector, you can observe the number of photons coming from the stars. Then from that you can actually determine the temperature of the star, the surface temperature of the star. Okay, so anyway, this is the same slide that they are showing that. Okay. So now let us try. So far we have understand the temperature of the stars through there, and we have using photometry, using different filters, and then and we have classified the stars like O, B, A, F, G, K, M kind of stars. The other classification we can also do based on the luminosity. That is so what is the total luminosity? That is, you add up the the total flux from all the filters, and then see how the object is more luminous or less luminous. Okay, so so typically in astronomy, what we do is that since sun is the closest star to us, and we understand sun more because since it is close to us, we have studied it more. So so what we do is that in astronomy and astrophysics, we study everything in ratio. That is, with respect to sun, whether a particular star is more luminous, more hot, or less hot, like that. Radius is larger, size is large, or size is small, is all with respect to the sun, because sun's luminosity, total brightness, is very well defined because it is closer to us. We can measure the total flux from the sun coming out very accurately, and so that is why it is considered as like as a standard candle. Okay, so with respect to sun, a distant star, whatever we are measuring, whether it is more bright or less bright, like that. So this is your y-axis. So you can actually see this is the sun's point, and you can see this is one. That is one solar luminosity. Okay, and you can see this is logarithmic scale. It's 100, 10,000, 1 million. Similarly, 100th and 1,000th. So you can actually see how the star's intrinsic brightness varies. So you can see there are stars which are, can be 1 million times brighter than the sun. And as well as there are stars which are like 1/10,000th of the sun in terms of brightness. So, this plot actually shows that, and it can actually tell you that distribute that. From this, we can actually learn what are the various physical properties of the stars. Okay, so again, this is the same diagram with temperature and luminosity. Here is the sun. You can actually see typically, like if the stars, what is the source of the energy from the star? The source of energy with the star is basically nuclear fusion. So, nuclear fusion is basically, you have 4 hydrogen atoms combining together, forming 1 helium atom, and the total mass, if you consider Einstein's equation of E equal to mc square, where energy is equal to mass times the c square, where c is the speed of light. So if you see the total, since we have total of 4 hydrogen atoms, and combining together, you have when you combine 4 hydrogen atoms, you get 1 helium atom. That is the nuclear fusion. And when such a thing happens, what happens is that the total energy, if you convert the entire energy mass of the 4 hydrogen atoms into energy, and if you consider the energy from coming out from the total mass of the helium, that energy is slightly less than total 4 atom energy of hydrogen. So which means that when you are combining 4 atoms of hydrogen and converting into a mass of helium mass, there is some energy difference. That is the energy that is used to convert combine the 4 hydrogen atoms to 1 helium atom. That energy is slightly less than the total energy of the 4 helium atom. So that means you get some surplus energy, and that surplus energy is released in terms of heat and light from the star's core, because the nuclear fusion is not happening at the surface of the star or sun. It is happening inside the at the core of the sun or the star. So that energy is radiated, and that's why the sun, it glows, and like we see the sun or stars emitting light, because of that small energy difference. So what happens is that when so what happens when like as I said, that you have 4 hydrogen atoms combining together and forming 1 helium atom. So if this process is going on continuously, so obviously, like if you when you put petrol or diesel in your car, the tank is full, so the car will run as long as there is fuel in the car. Once the fuel empties, fuel is over, then what happens? The car stops. Similarly, when when all hydrogen is exhausted, that is, all hydrogen is converted into helium that is there in the core of the sun or the star, then what happens? No longer fusion happens. So which means the nuclear fusion stops, which means the energy production stops. So which means that the star no longer is producing energy, so something else is happening. So let me just tell you what happens then. Okay, so what happens is that when such a thing happens, basically what happens is that there is no sun. There is no hydrogen inside the. Let us take the example of sun. There is no hydrogen inside the core of the sun. So what happens is that nuclear fusion stops. So usually when we see the sun as a fireball. So when there is a fireball, what happens is that sun has the mass, so it has a gravity, and then because of the fireball, you have high temperatures. The surface is 5,800, as I said, and inside the core, the surface temperature is 10 million degree Kelvin. Okay, close to 10 to the power of 7 Kelvin. So what happens is that there is a heat and pressure. This heat and pressure is balanced by the gravity, and that's why you get a fireball and you get an equilibrium. Okay, if there is no gravity, then because of the heat, the gas will disperse. But because of the gravity, the gas is hold together by the gravity, and the diameter of the sun is defined by the equilibrium between the pressure because of the heat, high temperature inside the sun, which is balanced by the gravity. Now, what happens? Very interesting thing happens when the sun exhausts hydrogen. No nuclear fusion happens, so there is no heat. So obviously, when there is no heat, the central part of the sun collapses, and what happens is that because there is no heat, so therefore the gravity wins over the pressure. The core collapses, but at the same time, as the core collapses, it generates by the process of collapse itself, it generates kinetic energy, and that kinetic energy is converted into heat, in which actually creates more energy on the in the outside the core, and from where you get into the kind of the star blows up. I will show you in my future this thing. Yeah, this is what I was trying to tell you, is that this core collapses, and then you have this hydrogen fusion happening in this is the total star diameter. Okay, so this is what happens is that this helium core, no more thermal reaction happens, and you have, so as this core collapses, this one goes this region actually gets heated up, and hydrogen, but here you have hydrogen. Earlier fusion was happening only here. Fusion doesn't happen everywhere. It only happens where the temperature is 10 million Kelvin. Temperature is 10 million Kelvin only in this small region. This is where this fusion happens. When all hydrogen is finished here, but you have hydrogen here. So what happens is this collapses, and you have this part heating up, goes to the level of 10 to the power of 7, and then hydrogen fusion starts happening here. So as a rate, what happens is that there is more heat generated in this area, so the star actually blows up. The star actually blows up. So suppose today's sun size is this, okay, and this is the Earth's orbit around the sun. So what happens is that when the sun hydrogen gets exhausted from the star's core, so then the shell burning happens, and the star blows up, and as it blows up, it goes into the giant phase, because the star becomes very large, and it will become so large that the sun actually will engulf the Earth itself. So the Earth will be, at that time, Earth will be destroyed. So don't worry, this will happen after about 4 billion years from now. So we have enough time. Okay, so this is known as the red giant phase. Okay, so what happens is that if for kind of this is another example actually. This is the star and this is the core. So you have helium. So when the star is actually so now when what happens is that you have helium here, here, and hydrogen burning here. Now, in case of sun, the sun mass is not very large to have enough high temperature to burn helium. That is, just like you have hydrogen fusion from going from hydrogen to helium. Helium can go into formation of carbon. and energy. But to do that, you require about 20 million Kelvin. But 20 million Kelvin sun is not very large to go, the temperature can go up to 20 million Kelvin. So in sun, when the sun's will become an old star after 4.5 billion years, so it will only have a helium dead core and the shell burning for some time, and the solar system will be destroyed, and you have a like a helium kind of star kind of thing instead of hydrogen star. Okay, so typically for some like sources, you have this kind of this is your present stage. So after a few billion years, it will become a little larger, and then almost at 4 billion years, it will become very large, and then it will become so large that the sun's radius diameter will almost touch Jupiter radius. Okay, 5 AU kind of thing. And then what will happen, the mass will slowly will be ejected away, and you will get what you call as planetary nebula, and then you get a central white dwarf, which is the core, and then you get this kind of gas ring kind of gaseous structure that was ejected from the sun-like star. So this is what happens. So then again on the mass luminosity scale, you can. So initially star position currently is now here. It will initially, because it will become a giant, it will become very large. Therefore, its luminosity will become 10,000 more times than what it is to now. And at that time, it will engulf Earth and all the planets. And then it will shed all its envelope mass, and the core will only remain, and then it will become a white dwarf. Okay, so I will just skip this slide. I'll keep this. So okay, so this is the typical planetary nebula that we can see today. Like you can see the the white dwarf here. You can see all the gases being exhibited out, and they produce beautiful colors actually. They look very beautiful. Although the place may be very dangerous to go, but they look from distance very beautiful. But please understand that this is the future of our solar system after 4.5 billion years. Okay. Okay, so this is we have talked about stars that are sun-like stars. But I told you that there are stars which are many times larger in diameter and mass of the sun, like 10 times larger than, 20 times larger than sun in terms of mass, and in terms of radii, maybe 50 times more. And their surface temperature is like 50,000, like O-type stars or B-type stars. So what happens there? So they are actually, because they have enough mass, they continue to burn beyond helium. So I'll just talk about that. So here you can see that you have hydrogen fusion, where like you need 4 into 10 to the power of 7 type kind of temperature. Then the helium fusion, you need 2 into 10 to the 8. Then carbon fusion, you need 6 into 10 to the 8 temperature. Neon fusion, like that, you can go all the way up to actually, silicon fusion, which produces iron. You cannot go beyond iron. Okay, and so yes, so this is how this whole, like this is the star, and the core itself has so many, from the top you have non-burning hydrogen, hydrogen fusion, helium fusion, carbon fusion, and then oxygen fusion, neon fusion, magnesium fusion, silicon fusion, and in the center you have iron. When you reach iron, which means it's a bad news for the star. That is, no more fusion can happen. Okay, these are the various nuclear fusion, this thing, yeah. How iron is being produced at the center of the core. So you have helium. We have already talked about helium. Four hydrogen atom forming one helium atom. Then helium and carbon combining oxygen, helium and oxygen combining forming neon, helium neon combining magnesium. Like that, all the way you can go up to iron. You cannot go beyond iron. The reason is this, that if you can consider mass, again this is all based on Einstein theory of relativity, which is E is equal to mc square. So that is what is the total energy released from the mass of the atom. So this is the mass per nuclear particle, and this is the atomic number. So you have you can see this is hydrogen, this is iron, and this is uranium. So what happens is that as every time, like you hydrogen to go to helium, helium to carbon, oxygen, and as it approaches oxygen, like the total mass per nuclear particle is decreasing from hydrogen to iron, which means that when you go from hydrogen to helium, helium to carbon, or carbon to oxygen, and oxygen to silicon, magnesium, calcium, and finally to iron. Okay, each time you are forming a heavier element, what happens is that the total energy required is less than the amount of energy you had. So therefore, this fusion nuclear reaction is possible. Once you cross iron, you can actually see that the energy per is increasing actually. Okay, so you cannot go up. You cannot, you cannot violate the conservation of energy, the basic rule of physics, science. So, you cannot produce more energy than you have. Okay, it is like that. If you have X amount of money, if you have 100 rupees in your pocket, obviously you cannot spend 110 rupees or even 101 rupees. Okay, so similarly here, if you have some X amount of energy and you can form another nuclear higher element like carbon, helium, carbon, oxygen, or up to iron, and some extra energy remains and which is released. But once you go across iron, that process is not possible. So up to iron, you can form atoms very easily at the star core. Beyond that, some other process takes place to go up to, in nature, we have up to uranium. Okay, so that up to uranium, some other fast neutrino process and other accelerating process takes place, which is a different process. Okay, so the iron Fe core is under huge gravitational pressure, and since there is no fusion and cannot be supported by ordinary gas pressure, it is supported by electron degeneracy pressure, the electron pushing against the electrons. It builds up to the Chandrasekhar limit, which is 1.44 solar mass. Once it crosses that, the degeneracy pressure cannot sustain it, and the iron core begins to collapse. So when that happens, what happens? Every atom consists of the core where you have protons and neutrons. These protons and neutrons, they actually combine together and form everything converted into neutron, and that's how you get a neutron star. Okay, so once the neutron star is when everything is converted into neutron, what happens is that in the core there is some neutron degeneracy, like electron degeneracy. You have some neutron degeneracy, which actually balances against gravity, and it stops gravity from further collapsing the star core, and then you get neutron star. But if you go to very heavy masses, and this limit is around 5 solar mass core, means 5 times the mass of the sun. Once the core of the star is more than 5 times the 5 times the mass of the sun, then what happens? Even the neutron degeneracy is not possible to hold it. Then then a massive collapse happens, and the whole structure becomes collapse within a fraction of a second, and it becomes a black hole. So that is how a black hole is made. And this is the diagram of how, protons and neutrons combine together to form a neutron. The core collapse space is known to be so dense and energetic that only neutrinos are able to escape the collapsing star. Most of the gravitational potential energy of the collapse gets converted into 10-second neutrino burst, releasing 10 to the 46 joules, 10 to the power of 46 joules of this energy. Okay, I'll just tell you this, just a comparison, how large this 10 to the 46 joules is. Say, like US dropped, on Hiroshima, a nuclear bomb. Typically, the energy released on that is of the order of 10 to the power of 30. Okay, now you can see compared to 10 to the 30, it is 10 to the 46. Okay. So that kind of energy is about 10 to 44 joules is absorbed by the star production and explosion. The major unsolved problem. Okay, I'll skip this. Okay, so this actually shows that how, you can go all the way up to iron and different elements that are being produced. And so this is very important, and I think everybody should know this. The explosion drives a blast wave into the surrounding space. So a supernova happens. This is known as a supernova. Okay, the star goes fat, basically. It goes like a bomb. Okay, it blasts, and in which, about 10 to the power of 46 joules is released. Supernova explosions are the main source of all elements heavier than oxygen. And they are the only source of many important elements. For example, all the calcium in our bones and all the iron in our hemoglobin were synthesized in a supernova explosion billions of years ago. Supernova inject these heavy elements into the interstellar medium, thus enriching the molecular clouds that are the sites of future star formation and planetary systems. This enrichment process is what determined the composition of solar system 4.5 billion years ago. So as I said that the sun will live around for another 4.5 years, 4.5 billion years, sun actually have already lived 4.5 billion years. The total lifetime of sun is estimated around 10 billion years, around 9 billion years, out of which 4.5 billion years have been already spent. Okay, and in this 4.5 billion years, the past 4.5 billions, I think life appeared on Earth perhaps about 300 million years or about 400 million years back. Okay, so all the chemistry on Earth is possible because of this chemical enrichment from supernova from earlier generation stars before the birth of the sun. Okay, so typically this is an example of typical supernova. I will skip this. This is another example of a supernova. Okay, so it's, as I said, a lot of energy is being released. So you can actually see the star was hardly seen before the supernova was born. The star is somewhere here. And then once the supernova happens, for a month or so, it becomes very bright and then it again vanishes. Okay, so for example, this is a nearby galaxy, M51 galaxy. This is a famous supernova. You can spot it. Here it is. So in this picture, you will not see it, hardly see it, and this appears. Suddenly it appeared, this supernova appeared in 2004 or 2005 for like a month or so, and then it vanished. Okay. Yeah, it happened on June 28, 2005. So typically this is how it happens. So you have, our universe is consists of in our galaxies, various galaxies, and in galaxies like our galaxy is Milky Way, and you in the Milky Way you have clouds of hydrogen gas. Okay, so this hydrogen gas from hydrogen clouds, new stars form, and when new stars form, you have the stars are forming here, and then when the stars become old and big stars become old and they form supernova, and then they blast, and again the whatever iron, oxygen, calcium, strontium, whatever, nickel, all the materials, all the 92 elements that are put inside the stars, is thrown away, thrown into the space, into the molecular clouds, from where new stars born, and that's why the enrichment happens. Okay, so now I will come to the exoplanet part, the research that I do. I think I will take about 10 minutes, not more than that. So yes, see, I was talking about the stars. You look at the sky and take like observations. Do filter. You put various filters and try to measure the star temperature and all those things. In case of planets, it is not possible to do that. The reason is that is this. So if you consider like our solar system, this is the star's black body. Okay. And this is the Jupiter black body, and this is the blue color is the Earth's black body. You can see, because planets don't emit light from themselves, they are actually reflecting their host star's light. In case of Earth, it is reflecting the sun's light. In case of Jupiter, it is reflecting the sun's light. Okay, so they are just reflecting mirrors. So therefore, their brightness obviously is much less than the star or the sun itself. So typically, the stars, the planets, the brightness will be about about a billion times fainter. Okay, and so the Earth is about 10 billion times fainter than the sun, and Jupiter is about 1 billion times fainter than the sun. So which means that like say if suppose there is an alien star species. Okay, some alien creature who is traveling on a starship, and suppose I said that somewhere like I use the word 10 parsec, which is the absolute bend scale. Suppose this guy is supposed to say 10 parsec or 30-40 light years away from our solar system, and trying to figure out is there any planet? Are there any planets around this particular yellow star, which is our sun? And that fellow will have a hell of a difficulty to discover any of the planets. The reason is that like the planets will be so faint compared to the star, and so the star brightness will be blinding him. Actually, it is like firefly. जो जुगनू होता है, एक जुगनू को अगर आप अंधेरे में देख सकते हैं, लेकिन जुगनू को अगर एक लाइट हाउस के अगेंस्ट पे आप रख देंगे तो आप जुगनू को नहीं देख सकते हो, क्योंकि लाइट हाउस में से इतनी लाइट आएगी, आप जुगनू को नहीं देख सकते हो. यहाँ पे भी वैसे ही होता है. So it is not possible. So then how do you do that? Fortunately, like Mother Nature has given us some very beautiful ways, indirect ways to determine planets around stars. So what is it? You see, when a planet goes around the star, or the sun is going, Earth is going around the sun, it is not the Earth is going around the sun, or the planet is going around the sun. It is actually going around the common center of mass. Okay. Now, it so happens because the mass ratio, that is the mass of the star, is so large compared to the mass of the planet. So this point, actually, I have shown it to exaggerate it, but this point is almost very close to the star center, but not exactly close to the star. So what at the center of the star. So what happens while the planet goes around the star actually, like wobbles, like a toy.
Participants are requested to stay connected. We will soon resume the session.
Hello, can you hear me? Shall I continue?
Yes, sir.
Yes, sir. Please, sir.
So, okay. So what happens is that in case of, like star and planet, what happens if the star, if if the planet comes between the line of sight between the star and the and us, that is Earth. What happens is that a tiny fraction of the starlight goes away. So this is what happens. Okay. So so a bigger planet goes comes in front of the sun, not star, sorry. So a small amount of dip happens. And
Sir,
you can get the dip. Can you see this?
sir, no, sir. We cannot really see your presentation any longer.
Okay, okay. Maybe वो चला गया क्या? अच्छा चला गया क्या?
You can share your screen again, sir.
Yeah. Can you see it now?
Yes, sir. Visible. Perfect.
Okay. Okay, so did you see this slide? Did you see this slide?
Before the glitch happened, this was there.
Okay, okay. Okay, so what happens is that when we are in line with the planet, and this for this to happen, you need the star, the planet, and the Earth has to come in one line. जैसे ग्रहण के वक्त होता है, ऐसे इसमें भी स्टार उसके बाजू बाजू जो प्लैनेट जा रहा है वो, और हम मतलब हमारा अर्थ, हम अर्थ में है तो अर्थ, it has to come in one line. If it comes in one line, and that is the plane of the rotation of the planet going around the star is in our line of sight, then what happens is that you will see the planet going around the across the disk of the star. But you know the planet is very small compared to the star, so it only blocks a tiny part of the star, and so you will see a small dip in the in the intensity of the flux of the star. Okay, if the planet is large, you will see a larger dip like this. Okay. So therefore, thus the dip is directly proportional to the radius of the planet. Okay. So see how from small things we can derive very interesting parameters. So this when such an event happens, you can actually measure the radius of the planet that is going around the star. Okay. Then the other thing I described you is the radial velocity. That is the wobbling, Doppler wobbling effect. So that the star is going around the common center of mass, and the planet is also going around the center of mass. So what we observe in that case from Earth is we cannot observe the planet, but we can observe only this yellow color star, which we can only see it is swinging like a pendulum. So we build spectrographs to measure the swinging of the star. Okay, so as we see, measure the swinging of the star through Doppler velocities, so we can actually, you can see that you can actually see this sinusoidal motion of the star. So what happens is that the mass of the star can be measured from the amplitude from 0 to whatever is the maximum. This amplitude gives us the mass of the planet, and the orbital period gives us the period of the planet going around it. And say, using Kepler's third law, from the period we can find out the semi-major axis, that is the distance between the planet and the star. So you can see that if you combine two effects, one is the transit method, another is radial velocity. By combining this, you can get all the parameters of the planet without actually seeing the planet. That is the mass of the planet, the radius of the planet, as well as the how far it is from the star, and what is the period of the planet. Okay. So this is a small mathematical equation which shows that, how we can do this. Okay. And okay. So this is a very interesting slide. It says that, ultimately our interest to know whether are we alone in the universe. Is there life in on other planets? Okay. Outside our solar system. So, so to have a planet, life on a planet, one of the main thing is that, the temperature. The first thing is there are many important factors. Of course, there has to be like a good atmosphere. Then, there has to be if we assume that life is similar to our life, then of course life can be some unknown kind of life, we do not know. But assuming that life is similar to our life, that exists on Earth, or like carbon-based life. Our life is basically carbon atom-based life. Okay, or we are made up of carbon organic materials, which is mostly carbon, hydrogen, oxygen. Okay, of course there are hypothetical argument that you can also have silicon-based life, but I'm not going there. So you have this carbon-based life. So to have a carbon-based life, the first necessity is that, the stability of organic molecules. The stability of organic molecules is typically from, say, minus 50 degrees Celsius to plus, 60 degrees Celsius. Okay, in that region, in this region, you can have, you can have some form of life. Say, for example, we know that deep down in the Pacific Ocean, when there is no sunlight, near volcano, very high water temperature of 60 to 70 degrees Celsius, people have discovered bacteria, okay, or some kind of very low level animals. Okay, so life. So that is one limit. Similarly, if you go in Antarctica at very low temperature of minus 50 degree or 60 degree, people have seen some kind of algae or something like that surviving somehow. So if you consider this extreme range of minus 50 or minus 60 to plus 60, so our first assumption will be that that the distance between the planet and the star should be comfortable, where the temperature, surface temperature of the planet should not be too hot or too cold, and the temperature range should be minus 50 to minus 60 to plus 60. Okay, so that region is called a habitable zone, and by calculation you can see this blue region is basically the habitable zone. And you will be, of course, on top of this you have the atmosphere that actually helps. Actually, for example, you can see Mars is more in habitable zone than Earth. However, because of Earth's atmosphere, it is more habitable, okay, than Mars, because Mars has hardly any atmosphere. Okay, so this is another very important this thing, and Venus is way away actually. See, so that is why we should be very worried about our climate change issues, and it's very important. The greenhouse effect gases, they can actually make Earth into hell, because we are already near the very actually at the border. Okay, so now I can actually see there are very handful of such planets that are out of 5,000 so far discovered. Only a handful of them we know which may be in the habitable zone, and they are not even Earth-like planets. They are like gaseous planets. So obviously life on them is not possible, or maybe completely different than ours. We do not know. We do not know anything about them. But this is how a habitable zone concept is defined. Now I want to tell you is that radial velocity, I talked about the radial velocity, right? So this amplitude part. So I told you that amplitude is directly proportional to the mass of the planet. Okay. So now what happens is that you can actually see that because of Earth, sun and Earth combination, the sun only wobbles around about 9 centimeter per second. Okay, and because of Jupiter, it wobbles around 11 meter per second. Okay, now here is the interesting thing is that when you actually make a spectrograph to measure this kind of precision measurements of 1 meter or less than 1 meter, it is extremely difficult because your spectrograph is very large. I will show the spectrograph here. This is the Paras spectrograph that we built in Mount Abu. Okay, this spectrograph is inside the vacuum chamber and under vacuum. Why? Because if you, if there is a change of temperature of 1 degree Celsius in the ambient, then what happens is that the spectrograph will shift because of change of refractive index within the glass components and the air will shift by 100 meters per second. Similarly, like if there is a change of atmospheric pressure in the air of 1 millibar, okay, 1 millibar. Note that like our atmospheric pressure is 1000 millibar, 1 atmosphere, 1 bar. And then, like in that 1 bar, you always, you get low pressure, rain, this, that, high pressure, cold wave, and all those things. And typically the pressure, atmospheric pressure will change by, 50, 60 millibar, around 1000 millibar. And with 1 millibar difference, the spectrograph lines may shift. The spectrograph lines, these are spectrograph lines. They will shift by more than 100 meters. That means you will assume an artificial shift of 100 meters, whereas you require less than 10 meters to detect even Jupiter. Okay, and to detect Earth-like, you need 9 centimeters. Okay, so that is the issue, and so therefore they have to be in vacuum and in temperature control. So so we assume we actually have achieved about for Paras 1 and in future Paras 2 on the 2.5 meter telescope, we achieved about 0.001. That means 1 millikelvin at 24 degrees Celsius stability, which is extremely difficult to get. So that we can intrinsically get down to level about 30 centimeter. That is this. Yeah. So you can actually see this is the 10 centimeter limit. This is a 20 centimeter limit. This is the 30 centimeter limit. Today around the world, most spectrographs, are around 50 about 1 meter, which will not shown here. And what we are trying to achieve is about 30 centimeter. So we will be able to, detect planets in this range. So Earth is still far away. And I will also tell you why this is so difficult. Okay. So this is a typical, star spectra where you can get these absorption lines, and this is how the oscillation of these lines actually gives us the measurement of the star wobbling, the pendulum oscillation of the star. Okay, so why it is so hard to go to sub 1 meter per second? See, that is because when the light is dispersed on the detector, so this is the light is dispersed. So what we are measuring is length, basically. Okay, so when you have a prism or you have a grating which is dispersing the light, and you are dispersing the light on the detector, which is a CCD detector, like a camera in your cell phone. Okay, and and you get the stellar spectra like this. Okay, so how precisely you can determine these absorption lines is what it means, which means that basically you are trying to measuring length where 10 centimeters per second is actually correspond to like few atoms of silicon. Because why I'm saying silicon? Because most of the detectors are semiconductors. They are actually made of silicon atoms. So basically, you are trying to measure the distance between few silicon atoms. Like this is the lattice of the silicon atom. So this is 1 nanometer. So you can see this is 1 nanometer. So 10 centimeter is basically equal to 2 nanometers. So that means if you want to go here, if you want to go down to this limit, you need to determine measure distances precisely about 2 nanometers or 1 to 2 nanometer distance. That is the problem, and that is what is the technical challenge. But fortunately, we have reached up to this level, which is about like you can say that maybe factor of 5 more. That is like maybe about 20-30 nanometers precisely we can determine, but going below that is difficult at present technology. Okay, so now here I want to tell you is that in 2016, the power spectrograph which we have built, there was a Yale University, there was a global velocity limit precision on major ongoing programs, and in that, even though our telescope was on a humble 1.2 meter telescope, where some of these were on 10 meter or 5 meter class telescopes or 4 meter class telescope, we were still was the third most precise spectrograph, doing it at 1 meter per second. And in 2016, the best spectrograph was able to do 80 centimeter. Remember, just now I was talking of 30 centimeter, but in 2016, the status was that the best spectrographs were able to do only 80 centimeter precision, and we were at a level of 1 meter. So now, based on Paris, we had discovered two planets so far. Okay, this was the first discovery of the planet from India, and which was about 27 Earth mass size and radius of 6 Earth radii, and it has a period of 19.42 days. Okay, and then we had last year discovered another planet, which is about 0.7 Jupiter mass, and radius is 1.44 Jupiter radii, and it is density is extremely small. It is one of the least densities, 0.31. Okay, whereas Jupiter is 1.33, and it is very hot. Its temperature is close to 2000 K, and the separation is 0.00449 AU, and in case of Jupiter it is 5.2 AU, which means that this is at Mercury, distance of Mercury and Sun is 0.4 AU. Okay, and this is 0.05 AU. So basically, this is almost 1/10 of the distance. So it's very close planet. Okay, so these are the two recent discoveries we have made about planets. We also discovered some brown dwarfs, which are failed stars, which are neither planets nor stars. We have discovered a couple of them. Okay, now the future is the 2.5 meter telescope and Paris-2. This telescope is now ready. So this is Paris-2, and the Paris-2 is now working at a resolution of 100,000. Actually, it is close to 110,000. And it has already seen the first light with the telescope, and it will be operational for doing science by January next year. And it is the highest resolution spectrograph in the country, and also few among the world, and also the first also in Asia. And so this has a capability of 30 centimeter per second. This thing. So we have made improvement from 1 meter to 30 centimeter. Okay, so this is a comparison between Paris-2 and Paris-1. So this is the complete spectra of Paris-2, and you can see the same region in Paris-2 is very well resolved, and in case of Paris-1, it is not well resolved. So this actually gives us advantage and gives us a possibility to go down to, as I said, that we are able to differentiate more closely the lines, not up to 10 centimeter, but we have already demonstrated to go down to about 35 centimeter per second. Okay, so So yes, so with this, we plan to look for planets that may be in this region, and hopefully in the next 5 years to 10 years will be very exciting for us. So with this, I stop here, and if there are any question, I'll be ready to answer.
Thank you very much, sir, for such an informative session talking about stars and exoplanets. Students, if you have any questions, you can put in the chat box. Once again, I request Darshan Desai, sir, to kindly summarize the talk for today.
Students, if you have any questions, I would like to hear from you first. In fact, sir, it was great to hear you on these topics. In fact, the talk that you gave complements, like the course on astrophysics that we teach over here and yours, the talk that you gave, complement each other very well. And I'm sure students were able to grasp a lot of things from. Sir, I know very little about these things and wanted to do one thing. For radial velocity method that you showed, what happens to the other planets that are around, the planet that you're trying to look for?
Yeah, that's a very good question. See, to make it simple, I actually showed took an example of like one planet going on, because then it is a simple sinusoidal. In case of the more number of planets, it becomes a very complicated motion, and you need to do like you need to take a lot of data. Actually, probably like it is not easy to detect this kind of planets. Planetary systems, sometimes it takes 5 years to detect one planetary system, because if there is some 3 planets, suppose one has like 6 months period, another is 1 year period, another maybe 1.5 year period, then you need to actually take lot of data over a period of 3 years, so that you compile all the period, and then do a numerical fitting of the data properly, and then what you do is log-Scargill method, by which like FFT analysis, you can find out what are the various periods that are, and then you can get separate individual periods. That is what it is. It's a very involved mathematical technique.
Right, sir. And like mostly you must be combining the 2 methods, right, to find out, also.
Yeah, in case like one of the see, there is a lot of serendipity involved. If you do only radial velocity, you do not know whether there is a planet around it or not. Okay, you may observe for 2 years, and then you can say, अरे इसमें तो कुछ है ही नहीं, ठीक है? तो पहले ऐसे ही होता था, लेकिन जब से we have this, like you have this global satellites, Kepler satellites, TESS satellites, and future Plato satellite will be also coming. They survey, millions of stars together. Okay, and over a large period, and then give us what is the probability of the planet transiting around it. Okay, so there is a International Astronomical Union rule, IAU rule, is that the credit discovery goes to that team, which actually proves that the false positivity probability, that is, false positivity probability is defined as the probability that it is not a planet but something else, though it appears to be a planet. Okay, that is less than 1%. Okay, so in order to do that, once this candidate comes, we have to do several months or years of observations using radial velocity to prove that, okay, this is not something else, it is only planet. Okay, so therefore that's how the discovery goes into the team which does this follow-up observations. Okay, that is the usual procedure.
Right.
And so because of the transit thing, so you get the like the radius of the planet.
Right, sir. That is very true. Which is very important as well, right?
Because you know the density.
All right. Any other questions? You can also unmute yourself if you wish to. And okay. So, sir, if there are any questions, we'll email it to you. We'll forward
sure.
the questions to you at some
Sure,
point.
sure. I was not aware that you people have a astrophysics course.
Yeah, actually, about a year or so, we just started, giving this course to the students. We think this is astrophysics is picking up very quickly over the last decade. I think it has grown exponentially, and
Yes.
something that cannot be avoided any longer. It seems the challenges that the field has are also like very interesting, and a lot of students here are like really interested in learning more about stars and stuff like that.
So I think, like then you should encourage them, we can talk about this actually more. You should encourage them, like visit PRL or the Mount Abu Observatory.
Certainly.
Okay.
Sir.
And,
They had been to Mount Abu when I think this thing was like being installed. This 2.5 meter telescope was being installed. We also tried going to the Udaipur Observatory, but they were not like accepting the students at that point of time because of this COVID and everything. But very soon,
yeah, the COVID was
exams are over.
yeah. Plus, we have all this wild animal issue at the observatory. So nighttime we usually do not allow because we have bear and leopard issue in the nighttime.
All right.
Yeah.
All right. So, may I hand over the session back to Nikita, ma'am?
Yes, sir.
Shall we? Yeah. Hemal sir, can you share your screen?
Yes, sir.
Sir, on behalf of the Mehsana Urban Institute of Sciences, we would like to present a small token of gratitude.
Thank you very much. Thank you very much. I
We are really
appreciate.
grateful, sir. We'll stay in touch, and the
Sure.
session that you gave was like highly informative, and I'm very sure that it has helped our students a lot. So thank you very much, sir.
Thank you. Okay. And you please let me know if if you are sending our story, your students here or something like that.
Sure,
Also,
sir,
I will encourage at what level your students are actually doing, at BSc level or MSc level?
Both, sir. We have up
Both,
to
sir.
PhD.
So, okay, you have PhD also.
Also, sir.
Okay, so I think like there should be because we also have some mandate of science popularization. Okay, PRL has a mandate now. Government is like pushing in those directions. So I think like you should encourage your people for summer internships here in.
Definitely,
in
sir.
PRL.
Definitely.
Okay, every year we take some. अभी कोविड के लिए बंद हो गया था बीच में, पर अभी चालू होगा अगले साल या अगले साल तो डेफिनेटली होगा.
Sure. Certainly. Thank you very much, sir.
Okay, bye.
Thank you, sir. Bye, sir.
Bye.
So let us then move on to the closing ceremony.
Yes, sir.
Right. So students, without you, this would not have been possible. So thank you for being part of this entire process. I believe it has been very useful to you, and I hope now that you see how the stuff that you learned in classes are connected to the frontiers of research. That would have increased your belief on what is being brought to you and in the utility of everything that you see in classes. I think you'll work even harder, and as Abhijit sir said and Munjal sir said, try your best to we will connect you to such institutions, and you can actually grow even more with the help of facilities that they have. But then for that, you have to study very hard, right? You have to learn about these things, and your core concepts should be absolutely clear. So that is all from my side, and just wanted to thank you. I will hand over the session to Nikita madam. She is going to announce the winners of the 3 competitions that we had on 8th of August, right, which was a part of celebration of this program, the birth anniversary of Dr. Vikram Sarabhai. Right, so we had model-based competitions, right, which is parachute drive, balloon car race, and third one was the space vehicle model. Right, so we are going to announce the winners. Also, the winners for the live quiz will be announced. So keep your fingers crossed and best wishes to all of you.
So now we are about to begin with the closing ceremony of Antrix 2022. On this occasion, various technical and non-technical competitions were arranged by Department of Physics, MUIS Ganpat University, and we have received overwhelming participation from various institutes. So without taking much of your time, now we will be announcing the results. First, the results will be announced in 2 categories. For school students and college students. For school students in parachute drive race, the 3rd rank goes to Patel Vansh, Patel Neem, Meet Patel. The 2nd rank goes to Purvansh Bhatia, Chavda Dev, Ravikant Kushwaha. And the 1st rank goes to Desai Nihal, Patel Prince, and Prajapati Rhythm. Congratulations. Now, category college students. The results for parachute drive race. The 3rd prize goes to Anand Thakur, Jaiswal Ayushi, Jadeja Dhruvraj C. 2nd prize, Patel Chintan, Jaideep Kantibhai Kanani. And the 1st prize goes to Dhamelia Anurag. Yes, congratulations. Now results in the school level competition, balloon car race. The 3rd prize goes to Ozaria, Pateliana, Patel Priya. 2nd prize, Sangada Divya, Patel Vishwa, Makwana Jigisha. And the 1st prize in this category goes to Thakur Krish, Nikamveer, Rajput Nihal. Congratulations to all the winners and the participants. Next, results for balloon car race, category college. The 3rd prize goes to Vyas Udit, Patel Govind, Patel Himani. 2nd prize, Patel Smith and Patel Kirtan. And the 1st prize goes to Jagania Pawan and Patel Dhar. Congratulations. Now the results for space vehicle model competition, category school. 3rd prize winner, Dhruv Suthar, Rathod Naman, Panchal Devi. 2nd prize, Desai Ayushi, Thakur Kanisha, Mishra Ria. And the 1st prize goes to Mishra Ronak, Gadvi Avani, Patel Krina. Congratulations to all the winners and runner-ups. Next, please. Now, the results for space vehicle model, category college. 3rd prize goes to Bhankharia Yug, Jaideep Kanani, Chauhan Ritu. 2nd prize goes to Ami Patel, Rani Rohit. And the 1st prize winner, Chauhan Shwetaben, Thakkar Krishna, and Purvika Boya. Congratulations to all the winners. Now, today we conducted live quiz. And in this particular competition, category school, the results are here. The third prize goes to Devanshi Mishra, second, Jamsi Patel, and the first prize goes to Ishita Rao. Many congratulations. Next, please. Live quiz, category college. The third prize goes to Darji Yash, second, Yug Bhankharia, and first, Urvil Chaudhary. So congratulations to all the winners, runner-ups, and all the participations. Thank you once again for joining us and making this event a grand success. Now, last but not the least, I would like to invite Dr. Darshan Desai, sir, coordinator of Antrix 2022, to deliver vote of thanks. Please, sir.
Thank you, Nikita ma'am. I'll just take a pause of a minute or two. So today's event has been a wonderful event. And so was the one that we had on 8th, right? And heartiest congratulations to all of you, organizers and the students. Also, a very heartfelt thanks to the management, principals, right? Before I delve more into this thing, I would like to first express my gratitude for Honorable Dr. Ganpat Bhai Patel, Padma Shri Patron in Chief and President of the Ganpat University, to always be encouraging us to take up newer challenges. Right. We are also grateful to Dr. Mahendra Sharma, Pro Chancellor and Director General of Ganpat University, and Dr. Amit Patel, Pro Vice Chancellor and Executive Registrar of Ganpat University, for providing constant support and motivation. We offer special thanks to Dr. S.S. Pancholi, the Executive Dean FoS, for his constant support in planning and execution of such memorable events. Last but not least, we would also like to thank Dr. Amit Parikh, sir, Principal MUIS, Dean FOS, and Dr. Ajay Gupta, sir, the Director Research for Ganpat University, for always being with us. And they have been a source of motivation, support, guidance, and everything. Even so are our distinguished guests for today. B.S. Manjal sir from SAC ISRO, Dr. Abhijit Chakraborty sir from PRL Ahmedabad, who you just listened to. Great speakers, but they also take care of the content that needs to be delivered, and we truly had a great time listening to them today. And we had, as I said earlier, we had 3 model-based scientific competitions, one theme-based competition, which was live online quiz. And theme, as we know, was India's contribution to space exploration, right? We thank you all for wholehearted participation. Whether you're from school or university, on Vidyanagar campus, Ganpat Vidyanagar campus, or outside, we are truly grateful for your support and encouragement that you provide to us in planning and conducting such kind of events. A little bit about these things before astrophysics and stuff like that before I end my session is, this fields of astrophysics and space science have been fields of interest to us since very long now, right? They're immensely diverse. They have a lot of practical applications, and there is a huge scope of development in these fields, right? Not only this, the development that is being done is actually truly and directly helpful to the life, so to say, on Earth. So I hope that you have taken maximum benefit out of the knowledge and guidance that was offered, not only in the webinars but also as a part of your interaction with the judges during the competitions. And we will always be looking forward to having you in such sessions, right? With this, I would like to hand over the session back to Nikita madam, and we will have a university song played, right? So requesting Nikita ma'am to please conduct that part.
Thank you, sir. With this, we request everyone to kindly rise in the honor of Ganpati University song.
गणपत विद्यानगर तणा हमें तेज पुंज अविनाशी आधन्य धराना संतानो हमें सरस्वती अनुरागी आधन्य धराना संतानो हमें सरस्वती अनुरागी गणपत विद्यानगर गणपत विद्यानगर नवचेतन हम पगले प्रगटे आलस जड़ता त्यागी युग युग नांधार हरती नान जोत अहि जागी युग युग नांधार हरती नान जोत अहि जागी गणपत विद्यानगर गणपत विद्यानगर ज्ञान तना निर्मल प्रकाश थी धर धर उज्जवल करशु सत्य प्रेम करुणा छलकावी स्वर्ग भूमि पद धरशु सत्य प्रेम करुणा छलकावी स्वर्ग भूमि पद धरशु गणपत विद्यानगर गणपत विद्यानगर समाजनो उत्कर्ष साधवा हमें विद्या ने आराधी रहे न कोई दीन अकिंचन क्रूर दुष्ट हतभागी रहे न कोई दीन अकिंचन क्रूर दुष्ट हतभागी गणपत विद्यानगर गणपत विद्यानगर यज्ञ दान तप कर्म हमारा शाश्वत रहे प्रकाशी धरा गुर्जरी मात भारती थाशे धन्य सुभागी धरा गुर्जरी मात भारती थाशे धन्य सुभागी गणपत विद्यानगर गणपत विद्यानगर विवेक विद्या पराक्रम थी अंबर आंबीलैषु सुजलाम सुफलाम धरती माना चरणे जीवन धरशु सुजलाम सुफलाम धरती माना चरणे जीवन करशु गणपत विद्यानगर गणपत विद्यानगर
Thank you, everyone. Have a great day ahead.
દર્શન
Yes, sir.
આપણે staff members will remain connected. Let others
Right,
lead.
sir. Sure. As instructed by principal, sir, I request all the students to please leave the meeting.
Vanjal sir, are you
Students,
there?
please leave the meeting.
Vanjal sir connected છે?
Yes, sir. Hemal sir, I think without reporting students, we can remove them from the meeting if they are.
Yes, you can remove rest of the people.
Yes, sir. Yes, sir. I am actually working on it.
Sir, I think now there is no students present in the meeting.
Fine. હવે બધા કેમેરા ઓન કરીને બેસો અને એકાદ ક્લિક કરી દો એકાદ જણ. ખુશી કોણ છે?
Somebody must have joined.
મનાલીસાના બે આઈડી છે.
હા સર, એ ફોનમાંથી ને એવી રીતે લેપટોપમાંથી બે જગ્યાએથી જોઈન થયા છે. મનાલી મેડમ, તમારું લેપટોપ હિમલ સર જોડે છે?
મારું લેપટોપ તો સર બંધ છે, એટલે કદાચ ત્યાંથી ચાલુ કર્યું હશે. અને ફોનથી જોઈન થઈ છું.
ઓકે. હિમલ સર, કેન યુ ટર્ન ઓન યોર કેમેરા? મેડમ,
એક એકને કહેવું પડે છે. હિમલ ખત્રી અલગથી. ઓકે. Where is Mansi?
Sir, she has joined through desktop computer, so she might not be able to.
ઠીક છે. એક ક્લિક કરી દો, સ્ક્રીનશોટ લઈ લો.
Sure, sir. Sure.
This is the proof of the attendees. I think from the staff member only this many people have joined this event.
Sir, they were on and off. Actually, Kumar sir is at.
I'm not talking only about physics department. I'm talking about overall faculty and staff.
I have seen a few others. Paritos sir was there. Nikunjna madam from pharmacy was there. Nikunjna madam from pharmacy was here. And then Paritos sir joined.
સર કેયુ સર હતા,
I haven't
અજય
seen-
સર બી હતા,
કેયુ સર હતા.
પછી પ્રીતિ પાંડે મેડમ બી હતા.
હતા તો પછી છેલ્લે સુધી રહેવું પડે ને. Why they are not here till the end of the program? એક વસ્તુ બધાએ ધ્યાન રાખવાની છે કે we should be there till the end of the program. જ્યારે ગણપત યુનિવર્સિટી સોંગ વાગે ત્યારે બધા જ અહીંયા હાજર જોઈએ and everybody must switch on their camera during the ગણપત યુનિવર્સિટી સોંગ. આપણે લોકોમાં આટલી તો કોમન સેન્સ હોવી જોઈએ. તમે બધા પોતાની જગ્યાએ ઊભા થાવ છો કે નહીં ખબર કેવી રીતે પડે આપણને? હેલો મુંજાલ સર, ગુડ આફ્ટરનૂન. Munjal sir is driving car, I think.
Yes, sir. traveling, I guess. Acha, Hemal sir, look into the camera. I'll take one more.
Okay.
Click करेगा. Munjal sir, hello.
Yeah. There was some connectivity problem, so please go ahead.
That's fine, sir. Event is already over, and thank you for your cooperation and support, sir.
Oh, so nice of you. So nice of you. I'm really, always getting a pleasure, interacting with the Ganpat University. Thank you very much for giving me this opportunity.
And your session was very interesting.
Oh, so nice of you. Really, I try to, make it simple because it is a difficult subject, but that's why the more videos were covered and we can keep going like that. No problem.
Everybody must have enjoyed your session. Thank you, sir.
So nice of you, sir. So nice of you.
Thank you, sir. So
Bye-bye. Take care.
You can leave, sir. Fine. Thank you.
Okay, bye-bye. Take care.
Bye, sir.
Good day.
એટલે
Achha, there is
what
a
I was
student.
talking about, every time I have to give some instruction at the end of the event because people are not remain connected till the end. હવેથી આપણે નિકિતા મોસ્ટ ઓફ ધ ઇવેન્ટમાં તું તો હોય છે જ બરાબર એન્કર તરીકે એટલે તને તો ખબર જ છે કે કોણ હોય છે ને કોણ નથી હોતું. Now every time you have to give me the report that how many of staff members have joined, how many of them live in between, and at the end how many are remain present. અને હવે પ્રેઝન્સ એટેન્ડન્સ એ જ લોકોની ગણાશે કે જે લોકો છેલ્લી મિનિટ સુધી હશે. આપણે છેલ્લે સ્ક્રીનશોટ લઈશું અને જેટલા સ્ક્રીન પર હાજર દેખાશે આપણે એટલા લોકોને જ પ્રેઝન્ટ ગણીશું. બરાબર, લોકો મન ફાવે ત્યારે આવે ને મન ફાવે ત્યારે છોડીને જતા રહે મીટિંગમાંથી. ધેટ ઇઝ નોટ એક્સેપ્ટેબલ. એક્સેપ્ટ એની જેન્યુન રીઝન. બરાબર ને? આપણે જો ફેકલ્ટી સ્ટાફમાં જ આવો રિસ્પોન્સ હોય, આજે આપણે 50% સ્ટાફ અહીંયા કોલેજમાં હાજર છે, તો આપણે અરાઉન્ડ વી આર 80 પીપલ ઇન્ક્લુડિંગ ટીચિંગ એન્ડ નોન ટીચિંગ. તો 40 જણા તો હોવા જોઈએ કે નહીં? And others are also are at home. They can join such event from their place. Even student participation પણ ઘણું ઓછું હતું આજે, દર્શનજી.
I noted.
કોઓર્ડિનેટર્સ અને ફેકલ્ટી તરફથી સ્ટુડન્ટને જે કમ્યુનિકેશન થવું જોઈએ ને એ પ્રોપર વેમાં થતું નથી એવું લાગી રહ્યું છે. And then now onwards we will give this responsibility to concerned mentor of that class.
That is exactly what I did, sir.
And they are responsible for their students. If they are not attending, they are answerable. તમારા અંડરમાં 30 છોકરાઓ હોય મેન્ટરિંગમાં, તો you have to take care કે ભાઈ તમારા 30 છોકરાઓ સેશન એટેન્ડ કરે. આપણે આટલા સારા સારા એક્સપર્ટ્સ બોલાવતા હોઈએ, એ લોકો આટલા સરસ 2 કલાકના સેશન થયા હોય અને છોકરાઓ એનો બેનિફિટ ના લેતો એનો શું મતલબ છે? સચ ઇવેન્ટ હેઝ નો મિનિંગ. પછી ખાલી કરવા ખાતર ઓન પેપર થઈ જાય છે ઇવેન્ટ, એવું છે. પણ જે એકચ્યુઅલી આપણો પર્પસ છે એ તો થતો નથી આમાં. એટલે પાર્ટિસિપેશન ઇઝ એક્સપેક્ટેડ ફ્રોમ એવરીબડી, નોટ ઓનલી ધી કમિટી મેમ્બર્સ. આ તો એવું થાય છે કે જે કોઓર્ડિનેટર હોય અને એની જે ટીમ હોય એટલા લોકો હોય છેલ્લે સુધી. વોટ અબાઉટ અધર્સ? ધીસ ઇઝ નોટ વન પર્સન ઇવેન્ટ. આ કોઈના ઘરનું ઇવેન્ટ થોડું છે. It is our institute event and everybody must be here only. બરાબર ને? કાં તો પછી હવે મારે એવું કરવું પડશે, સ્ટાફને રેન્ડમલી કોઈને કોઈ રોલ આપવો પડશે. Any staff member will be given any role at any point of time during the event. તો જ બધા એટેન્ડ કરશે અને એટેન્ટિવ પણ રહેશે. We will start asking questions in between. We will arrange some quiz for the faculty and staff also. એવું કરી શકાય કે નહીં? આપણે એવું કરીએ નેક્સ્ટ ટાઈમથી, આ જે સેશન હોય ને એના રિલેટેડ એક ક્વિઝ આપણે ફેકલ્ટી સ્ટાફ માટે જ બનાવીએ. એન્ડ દે હેવ ટુ અપિયર કમ્પલસરી. તો જ બધા એટેન્ડ કરશે અને ક્વિઝમાં અપિયર થાય એના બેઝ ઉપર આપણે એટેન્ડન્સ કન્સિડર કરવાની, એટલે રિસ્પોન્સીસ પણ રેકોર્ડ થઈ જાય. લોકો છે ને, પીપલ આર વેરી સ્માર્ટ. તો પછી આપણે
સર આજે કદાચ ટ્રાવેલ કરતા હશે કે એવું બધું હશે ને?
હે
આજે કદાચ ટ્રાવેલ કરતા હશે ને એવું હશે એટલે કદાચ એટેન્ડન્સ ને આ થયું.
દર્શનજી, યુ ડોન્ટ ટ્રાય ટુ પ્રોટેક્ટ યોર ફ્રેન્ડ્સ.
ના ના સર, એવું કઈ નથી.
અત્યારે છે ને ટ્રાવેલ કરતા, હજી તો 4 હવે વાગે છે, જવાનો ટાઈમ હવે થશે, બરાબર છે? એટલે ઠીક છે, we will see, look at to that matter. આનું રેકોર્ડિંગ છે ને એ મને શેર કરજો, એટલે we'll check how many of them were present. And okay, thank you everyone. Thank you Nikita, Darshan bhai and entire team physics department.
Thank you sir.
That master